2.5 million light-years from home, in the quiet, sprawling metropolis of the Andromeda galaxy, a star was shining. It was a bright point in its neighborhood, a large star that had burned for millions of years. Then, one day, it wasn't there. It did not explode in the brilliant, cosmos-shaking farewell of a supernova. It did not fade slowly over millennia like a dying ember. It simply vanished. In a slow, quiet fade-out, seen only in the ghost light of infrared, the star was silently swallowed by its own gravity. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. This isn't just a story about a star's end. It's a quiet disappearance that seems to go against the most settled rules of physics. The collapse of this star forces us to ask a question that feels like it belongs in stories, but now sits at the very edge of what we understand. What happens when something literally runs out of space? What happens when the fabric of reality itself seems to say, "No more room"? The search for an answer quietly stretches the idea of what reality itself can be. To understand the disappearance, we have to understand the star. For most of its life, it was a giant, with a mass around 13 times that of our own Sun. For millions of years, it lived in a perfect, gentle balance. Deep in its core, a furious engine of nuclear fusion relentlessly pressed atoms together, creating heavier and heavier elements. This process released a steady flow of energy, a constant outward pressure that pushed against the star's own immense gravity. It was a quiet war waged on an unimaginable scale, fusion pushing out, gravity pulling in. This balance is the essence of a star's life. But all stars are temporary because their fuel is not infinite. Eventually, the fusion engine in the core of a star like this one begins to slow down. It can no longer generate enough outward force to resist the crushing, constant pull of gravity. And when that balance is broken, gravity always wins. In the usual story of a massive star's end, what happens next is the most spectacular event in the universe, a supernova. The core collapses under its own weight in less than a second. This sudden collapse is supposed to trigger an unbelievable rebound, a shockwave of energy that ignites the star's outer layers in an explosion so bright it can outshine its entire galaxy for weeks. The star dies in a blaze of glory, scattering the elements it made across space, seeding the next generation of stars and planets. This is the expected, the normal, the way these things are supposed to go. But for this star, the explosion never came. The shockwave, for reasons we are still trying to understand, failed. It fizzled out. Instead of a brilliant bang, there was only a quiet retreat. The star's immense outer layers, with nowhere to go and no force to hold them up, began to fall inward, pulled toward the newly formed, impossibly dense core. The star began to consume itself. This was not a supernova. It was a failed supernova, a slow act of self-annihilation. The star didn't explode. It imploded, beginning the process of erasing itself from the visible universe. The vanishing of the star was not instant. It was a slow, cosmic fade, a departure documented in the faint whispers of light it left behind. Astronomers, looking through years of stored data, pieced together a timeline of the star's final moments. The first clue was unusual. Starting in 2014, the star began to glow brighter, but not in visible light. In the mid-infrared spectrum, which traces heat, the star's light increased by half. This was the star's final, quiet burst. The outer layers, shedding and compressing as they began their inward fall, heated up, creating a shell of gas and dust that glowed with the last release of energy. For about 2 years, this infrared brightening continued. But this wasn't an immediate, chaotic collapse. Deep inside the dying star, a process called convection was taking place. Think of a pot of boiling water, with hot material rising and cooler material sinking. On a stellar scale, this gentle churning motion in the star's outer layers prevented everything from collapsing at once. It gave the falling gas a sideways push. So instead of just falling straight down, the star's material began to spiral inwards, like water circling a drain. This created a vast, swirling disk of hot gas and dust orbiting the point where the core used to be. It was this disk, heated by friction, that was glowing so brightly in the infrared. The star was being taken apart piece by piece, its substance drawn into a slow, patient vortex. At the center of this vortex was the star's collapsed core, which had already crushed itself into a neutron star. But the fallback of material was relentless. Ton after ton, the star's own outer layers rained down onto the core. There is a fundamental limit in physics, a point of no return known as the Tolman-Oppenheimer-Volkoff limit. It marks the greatest mass a neutron star can have before its own gravity becomes completely overwhelming. As the debris from the failed supernova piled on, the neutron star crossed this threshold. In that moment, the final resistance ended. Gravity became absolute, and the core collapsed completely, continuing its fall into an abyss from which there is no escape. A black hole was born. Over the next few years, from 2016 onward, the infrared light began to fade. By 2022 and 2023, when the Hubble Space Telescope and the Keck Observatory looked at that patch of sky, the star was gone. Where one of the most luminous stars in Andromeda once shone, there was now only darkness, and the faintest glow from the last remnants of the debris disk slowly feeding the newborn object. The scene was complete. The star had vanished, leaving behind only a shadow in space. Now we turn from the star that was to the object it became. A black hole. The name itself is simple, but the idea is not. It is not just a dark object. It is a place where our understanding of reality is stretched. A black hole is a region of spacetime where gravity is so strong that nothing, not even light, can move fast enough to escape. This creates a boundary, a one-way door in the universe called the event horizon. Anything that crosses it, a planet, a star, a beam of light, can never leave. It is captured, destined to fall toward the center. But it is at that center where our description of space seems to break down. Albert Einstein's theory of general relativity, our best description of gravity, makes a strange prediction. It suggests that all the matter that falls into a black hole, the entire mass of the star, which was still about 5 times the mass of our Sun, is crushed into a single point of zero volume and infinite density. This point is called a gravitational singularity. Imagine taking a mountain, crushing it to the size of a grain of sand, then crushing that sand grain to the size of an atom, and then crushing that atom until it occupies no space at all, while still keeping all of its mass. That is the prediction. The star has, in a sense, run out of space to exist. This is the central puzzle. We can use analogies, but they all fall short. Think of a computer's hard drive. It has a finite capacity. You can store files until it's full. When you try to add one more, the system says, no more space. The singularity is what happens when the universe itself seems to run out of storage space for matter. It's a question written into the laws of physics. The matter that made up the star is not just hidden behind the event horizon. According to our best theory of gravity, it has been squeezed out of physical existence as we know it. Its location is no longer a definable place. It has been replaced by a hole in space-time, a point where space and time cease to be meaningful concepts. The star is gone, its substance converted into pure gravitational curvature. For a long time, this was seen as a strange but contained idea. But then, a quiet conflict with the other great pillar of modern physics would turn this strange idea into a deep and fascinating problem. But there is a problem. A quiet, universe-stretching problem. According to the other fundamental pillar of modern physics, quantum mechanics, the star cannot truly be gone. Its disappearance, as described by general relativity, seems to go against one of the most basic principles of the quantum world. To understand this, we need to talk about information. In physics, information is the unique state of every single particle in a system. Think back to our vanished star. It was made of countless particles. Each one had a specific set of properties: its position, its velocity, its spin. The complete list of all these properties for every particle is the star's information. It is the universe's ultimate ledger, a unique blueprint that distinguishes the star from anything else. A core idea of quantum mechanics, known as unitarity, says that this information can never be destroyed. It is a law as fundamental as the conservation of energy. You can scramble information, like burning a book. The information in the book isn't gone. It has been transformed and encoded in the arrangement of smoke, ash, and heat. In theory, if you could capture every single particle and reverse the process, you could reconstruct the book. The information is conserved. It is just rearranged. Here is the paradox. General relativity tells us that when the star collapsed, all of its unique information was sent to the central singularity and cut off from the universe, effectively erased. Quantum mechanics insists that the information must be preserved somewhere. The two great stories that describe our universe give opposite, mutually exclusive answers about the fate of our vanished star. This is the black hole information paradox. It is not just an academic debate. It is a deep and quiet contradiction at the heart of modern physics. For a while, physicists thought the information might just be locked safely inside the black hole. But in 1974, Stephen Hawking made a discovery that deepened the mystery. By combining quantum mechanics with the curved spacetime around a black hole, Hawking's initial work suggested that black holes are not completely black. They glow. Due to quantum effects at the event horizon, they leak a faint thermal energy, now known as Hawking radiation. This radiation causes the black hole to lose mass, incredibly slowly at first, but faster over time. Over unimaginable eons, a black hole will completely evaporate. And here was the problem. Hawking's early calculations suggested this radiation was thermal, meaning its properties seemed to depend only on the black hole's mass, not on the specific details of what fell in. The radiation from a black hole made from a star would seem identical to one made from a library of encyclopedias, as long as they had the same mass. The unique information about the original object did not seem to be encoded in the outgoing radiation. So, what happens when the black hole completely evaporates? The star's information wasn't in the radiation, and now the black hole itself is gone. The information has been deleted. For nearly 50 years, physicists have been working to resolve this puzzle, to find the missing information and understand how the laws of the cosmos fit together. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. That way, you won't miss the next chapter in our quiet journey through science. To solve the mystery of the missing information, physicists have explored a lineup of strange and beautiful ideas. Each one challenges our perception of reality in its own quiet way. One of the most powerful ideas is the holographic principle. This concept, developed by physicists Gerard T. Hooft and Leonard Susskind, proposes a truly strange solution. The information never fell into the black hole at all. The theory gets its name from a hologram, a two-dimensional surface that contains all the information needed to project a three-dimensional image. The holographic principle suggests that the universe itself might work this way. According to this principle, the information of our three-dimensional star was imprinted, or painted, onto the two-dimensional surface of the event horizon. The information isn't in the black hole, it is the black hole's surface. As the black hole evaporates, this encoded information on the surface is subtly transferred to the outgoing radiation, preserving it. In this picture, the 3D black hole we perceive is just a projection, a hologram of information living on its 2D surface. Another possibility suggests an even more fantastic escape route: wormholes and baby universes. This theory asks, what if the singularity is not an endpoint, but a gateway? The extreme warping of spacetime at the heart of a black hole might, in theory, connect to another place and time, or even to a completely different cosmos. In this scenario, the information from our collapsed star wasn't destroyed. It was ejected, passing through the singularity and into a new, baby universe, completely separate and inaccessible to our own. The cosmic ledger is balanced. The information is safe, just transferred to a different book in a different library that we can never visit. Finally, a third idea suggests we have misunderstood the black hole itself. This is the fuzzball proposal from string theory. String theory suggests that the fundamental parts of the universe are not points, but tiny, vibrating strings of energy. From this perspective, a black hole might not have a singularity or a sharp event horizon at all. Instead, it could be an enormous, tangled, fuzzy ball of these strings. According to this model, when the star collapsed, its matter didn't get crushed to a point. It was transformed into this gargantuan, planet-sized ball of strings. It has a real surface and a real volume. The information of the star isn't lost. It's stored in the complex vibrations of the strings that make up the fuzzball. The star didn't run out of space, it was just translated into the language of strings. So, which of these ideas is right? Did the information get painted onto the horizon, escape to another universe, or is it tangled up in a giant ball of cosmic strain? The honest answer is, the case is still open. In recent years, new clues have emerged that seem to point toward some version of the holographic idea. Complex calculations have suggested that Hawking's original conclusion about purely thermal radiation was likely incomplete. These new theories provide a mathematical way for the information to escape, encoded in subtle quantum connections between the radiation outside the black hole and the interior. It seems information does get out, but it's scrambled in a way that is almost impossible to read. Some now even think the paradox itself comes from a mistake in how we try to combine the two theories. But these are still ideas at the edge of what we can calculate. The final answer will likely require a full theory of quantum gravity, a single framework that can finally unite the world of general relativity with the quantum world. The quiet death of the star M312014 DS1 is more than just an astronomical event. It is a real-world laboratory for these fantastic ideas. The silent disappearance of a single, distant star has led us to the very edge of reality. It has gently forced us to question the nature of space, the fate of information, and the fundamental rules that govern existence. It reveals a universe far quieter, more intricate, and more mysterious than we ever imagined. The search for that star's lost information is more than just an attempt to solve a cosmic puzzle. It is a search for a new, deeper understanding of nature, one that can hold both the crushing gravity of a black hole and the delicate quantum whisper of a single particle. The star is gone. The quiet mystery continues. Hawking's black hole paradox has finally been solved. In the quiet, cosmic order of our universe, there are principles. Principles that feel absolute. Gravity guides the path of light. The speed of light marks the ultimate limit on travel. But perhaps the most fundamental idea of all, the bedrock of physical reality, is this: information can never truly be lost. You can burn a book or shatter a glass, but the universe, in its deep memory, holds onto the pieces. The information is not gone, it has simply taken a different form. This principle, known as unitarity, is what ensures our universe is a place of cause and effect, a place where the past informs the future. Without it, reality itself would begin to unravel. But for 50 years, a quiet contradiction has sat at the heart of physics. A puzzle born from the work of Stephen Hawking. A paradox so profound, it suggested the universe might, in fact, have a way to erase the past. And that process had a name: the black hole. This is the story of that 50-year journey. A story about a conflict between two foundational ideas: the permanence of information and the inescapable nature of a black hole. It's a story of a paradox that challenged physics, and the remarkable new understanding that has, at long last, shown us the way to solve it. What has been found reveals how information performs an elegant escape, pulling itself from beyond the point of no return. And in doing so, it has not just preserved a law of physics, it may have rewritten our understanding of spacetime itself. The unbreakable law. Before we can appreciate the problem, we must first understand the rule that seemed to be broken. When a physicist talks about information, they mean something more fundamental than words on a page. Imagine a single atom. It has a location, a velocity, a spin. This collection of properties is its quantum state. That state is its information, a unique fingerprint distinguishing it from every other particle. Now, imagine all the particles that make up you: the air in the room, the earth, the sun. The complete description of every single one of those particles is the total information of the universe. Quantum mechanics, one of the most successful theories in science, is built on the foundation that this total amount of information is constant. It can be rearranged or transformed, but the total sum never changes. This is an idea we can see in our own world. If you drop a glass and it shatters, it seems the information of the glass is lost. You can no longer drink from it. But in the language of physics, nothing has vanished. The exact position of every shard, every tiny vibration of sound, every bit of heat from the impact, all of that information still exists. If you had a way to track every one of those variables, you could, in principle, know everything about the original glass. The information is conserved. The classic analogy is the burning of a book. You set it ablaze, and it turns to ash and smoke. The story seems gone, but to the universe, no. The information that made up the ink and paper has been converted into the chemical composition of the ash, the paths of the smoke particles, and the frequencies of the light and heat radiated away. It's been scrambled into a state of immense complexity, but it's all still there. The universe remembers the book. This principle of information conservation is the linchpin of predictability. It is what separates science from magic. If information could truly be deleted, the link between cause and effect would be broken. The past would become unknowable, and the future would be random. The logical, ordered cosmos we observe would be an illusion. This is the first titan, the quiet, absolute law that information is eternal. And for most of the 20th century, nothing seemed to challenge it. But the universe is a strange place. And deep within it, an object was waiting. An object so extreme it would put this sacred law to the ultimate test. It was born from Einstein's theory of gravity, a prediction so bizarre even he was reluctant to believe it could be real. A place where gravity becomes absolute. The black hole, the immovable object. To understand the paradox, we must first journey to the edge of one of these cosmic objects. A black hole is what remains when a massive star collapses under its own weight, crushing matter down to a point of incredible density called a singularity. Surrounding this point is not a surface, but a boundary of pure, warped geometry. An invisible line in the fabric of spacetime. It is called the event horizon. And it is the point of no return. Think of it like a river flowing toward a waterfall. At some point, the current becomes so strong that no boat can escape being pulled over the edge. The event horizon is that point, but for light. It marks the boundary where the gravitational pull is so immense that the speed needed to break free is greater than the speed of light. And since nothing can travel faster than light, Anything that crosses the event horizon is trapped. This boundary is not something you could touch. If you were to fall into a large black hole, you might cross the event horizon without noticing. One moment, you could in theory escape. The next, you cannot. Every possible path now leads to one destination, the singularity. Inside the black hole, space and time seem to swap roles. The singularity is no longer a place in space. It becomes a moment in your future, as inescapable as tomorrow. From the perspective of an observer watching from a safe distance, things would look even stranger. As you approached the event horizon, they would see your clock appear to tick slower and slower, your image seeming to freeze at the edge, fading over an infinite amount of time. They would never see you cross. Here, the first seeds of the paradox were sown. In the 1970s, physicists developed a simple idea called the no-hair theorem. It stated that a settled black hole can be described by only three properties: its mass, its charge, and its spin. All other intricate details, the hair of whatever fell in, are gone from view. Imagine two different stars of the exact same mass, one made of hydrogen, the other of iron. If they both collapse, the no-hair theorem says the resulting black holes will be identical. The information about whether the star was hydrogen or iron seems to have been wiped away, at least from the outside. For a while, this was acceptable. Physicists reasoned the information wasn't destroyed. It was just hidden from our view, held safely inside the event horizon. The book wasn't burned, it was just locked in a room. And as long as that room existed, the information was safe. But then, in 1974, Stephen Hawking performed a calculation. He was studying the behavior of quantum particles near a black hole's edge, not trying to start a revolution. But what he found would ignite a quiet, 50-year firestorm in physics. He discovered that the room wasn't permanent. He discovered that black holes aren't completely black. The paradox, Hawking's calculation. Stephen Hawking's 1974 discovery showed that black holes evaporate. This was a shock. According to general relativity, nothing could get out. So how could they shrink? The answer came from uniting the world of gravity with the world of quantum mechanics. In the quantum world, empty space is not empty. It is filled with pairs of virtual particles that pop into existence and then annihilate each other a moment later. Hawking realized that if this happens right at the edge of an event horizon, it's possible for one particle to fall in while the other escapes. From the outside, it looks as though the black hole has just emitted a particle. The particle that fell in has a kind of negative energy, which reduces the black hole's mass. The escaping particle flies away, carrying positive energy. The net result is that the black hole radiates a particle and gets a tiny bit smaller. This slow trickle of particles became known as Hawking radiation. The process is astonishingly slow. For a solar mass black hole, it would take around 10 to the power of 67 years to evaporate, a number far longer than the current age of the universe. But the principle was what mattered. Given enough time, every black hole will radiate away its mass and vanish. And with that final vanishing, a deep question arose. The room where the information was stored would eventually disappear. So what happens to the information that was inside? This was the crisis. Hawking's calculations suggested the radiation was thermal and random. It carried no story of what had fallen in. The radiation from the hydrogen star's black hole would be identical to that of the iron star's black hole. When they were gone, all that would be left is this indistinct haze of radiation. The unique information would be gone, truly erased from the cosmos. This was the black hole information paradox. It placed two pillars of physics in direct conflict. On one side, Hawking's calculation, rooted in general relativity, suggested that information is destroyed. On the other, the foundation of quantum theory insisted that information must be preserved. They could not both be right. If Hawking was correct, the predictability of the cosmos was an illusion. The physics community was thrown into a quiet turmoil. This was a crisis that struck at the heart of reality. The physicist John Preskill was so sure quantum mechanics had to be right that in 1997, he made a public bet with Hawking and another physicist, Kip Thorne. Preskill bet that information escapes, while Hawking and Thorne bet it was lost. The prize was an encyclopedia of the winner's choice, from which information can be retrieved at will. For decades, the paradox stood as one of the greatest unsolved problems in physics. To solve it, scientists knew they would need a new idea. The solution, when it began to emerge, was stranger and more elegant than anyone had imagined. The solution: a mind-bending escape. The first major crack in the paradox came from string theory. In the late 1990s, physicists Gerard T. Hooft and Leonard Susskind proposed a radical idea: the holographic principle. It suggested that all the information inside a volume of space can be described by the physics on its boundary. Much like a 3D hologram is projected from a 2D film, our three-dimensional reality could be a projection of information stored on a distant, two-dimensional surface. This sounded like science fiction, but it had profound implications. If the information of a 3D space can be stored on its 2D boundary, perhaps the information of everything that falls into a black hole doesn't actually go inside. Perhaps it gets stuck on the 2D surface of the event horizon. If so, as the black hole evaporated, that information could be slowly imprinted onto the outgoing radiation and carried away. It was a beautiful idea, but it was just a principle. That changed in 1997, when Juan Maldacena discovered a mathematical duality called the ADS-CFT correspondence. It was a concrete, working example of the holographic principle. It showed a perfect equivalence between a theory of gravity in a specific kind of five-dimensional, saddle-shaped spacetime, ADS space, and a quantum theory without gravity on its four-dimensional boundary, CFT. The details are complex, but the consequence was this: anything that happens in the 5D gravitational world has a matching description in the 4D quantum world on the boundary. And that quantum world perfectly conserved information. Since the two worlds were just different descriptions of the same reality, the gravitational world, including its black holes, must also conserve information. This was the turning point. It was the first solid mathematical evidence that information was not lost. The discovery was so powerful that in 2004, Stephen Hawking publicly conceded his bet with John Preskill, presenting him with a baseball encyclopedia. Information, Hawking now believed, did get out. But the crucial question remained: how? The ADS-CFT model was a powerful tool, but it described a different kind of universe, and didn't give a clear picture of the escape mechanism in our own. The final, crucial piece of the puzzle arrived in 2019. The breakthrough was the concept of quantum extremal surfaces, and the islands they contain. To grasp this, we need one more piece of quantum mechanics: entanglement. It's a profound connection linking two or more particles, making them parts of a single system no matter how far apart they are. Remember the particle pair at the event horizon? The one that falls in and the one that escapes are entangled. As a black hole evaporates, it spits out trillions of these radiation particles, all entangled with their partners inside. The 2019 breakthrough, from physicists including Ahmed Almhiri, Netta Engelhardt, and Donald Merolf, was to calculate the entanglement entropy of the Hawking radiation, a measure of its information. They found that as you calculate the entropy of the radiation, you can't just consider the radiation by itself. At a certain point, you must also include a portion of the black hole's interior, a region they called an island. This island is a region deep inside the black hole that is holographically represented in the distant radiation. The information isn't physically crawling out. Instead, the information inside the island and the information in the outgoing radiation are two different descriptions of the same thing. The information exists in two places at once. Inside the black hole, but also encoded in the subtle quantum correlations within the cloud of Hawking radiation that has already escaped. This allowed physicists to recalculate the information in the radiation over the black hole's entire lifetime. The result was a graph known as the Page curve, first theorized by Don Page in the 1990s. The new calculation matched the curve perfectly, showing the entropy rising, and then falling back to zero just as the black hole vanishes. This is the exact signature of information being preserved and released. The paradox within these models was resolved. A new chapter. We began with a quiet contradiction that sat at the heart of physics for 50 years. Stephen Hawking, the man who started it all, gave us the problem. Black holes evaporate, but their information seems to vanish with them. Now, a path to a solution has emerged. A solution born from the strangest corners of theoretical physics, holography and quantum entanglement. The answer is that information performs an incredible escape. It isn't destroyed. It gets encoded, like a ghost, into the connections between the particles that escape in a mysterious island inside the black hole. The Hawking radiation is not random noise, it is a complex, holographic projection of everything that ever fell in. In principle, if you could collect every particle of radiation, you could reconstruct the book that was thrown in. The universe does not have a delete button. Information is eternal. The resolution of this paradox is more than an academic victory. It is a profound clue about the nature of reality. It suggests that spacetime itself may not be fundamental, but an emergent property stitched together from a deeper layer of quantum entanglement. The event horizon is not an information shredder. It is a holographic plate. Solving Hawking's paradox has not ended the story. It has opened a new, more exciting chapter. We set out to solve a problem about black holes, and in doing so, we may have found a key to understanding the essence of space and time. The journey is far from over, but the path forward has never been clearer. If this kind of calm exploration into the world of physics helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near a city, a forest, or somewhere quiet in between, feel free to share where you're watching or listening from. The point where space-time snaps and disappears. Imagine a star hundreds of times more massive than our Sun. A cosmic titan so huge its own gravity is a ticking time bomb. Now, imagine you're there to witness the exact moment it dies. This isn't just the story of a star's death. It's the story of the instant the universe around it breaks. The point where space-time itself snaps and disappears. This is the journey from a star of impossible scale to a hole in reality. A place where time stops and the laws of physics are brought to their knees. So what happens when the universe's most stubborn force finally gets its way? The universe simply gets out of the way, leaving behind a scar from which nothing, not even light, can ever return. The cosmic titan, life of a hypergiant. To understand how reality can break, we first need to meet the object capable of breaking it. Forget our Sun. A pretty modest star in a quiet suburb of the Milky Way. The star at the center of our story is something else entirely. It's a hypergiant, a celestial object so profoundly large that our minds struggle to find a foothold. Let's try to put its scale into perspective. If you were to replace our Sun with one of these titans, like the red hypergiant WO G64, its fiery surface wouldn't just swallow Mercury and Venus. It would extend far beyond the orbit of Earth, past Mars, and would even engulf Jupiter. A beam of light, the fastest thing in the universe, would take just a few seconds to cross our Sun. To cross this hypergiant? It would take hours. This star isn't just large, it's luminous. It can burn with the ferocity of hundreds of thousands of suns combined, a beacon of violent, brilliant light that outshines entire clusters of lesser stars. But this incredible power comes at a cost. Where our Sun will gently simmer for 10 billion years, A hypergiant lives a life that is brutal, chaotic, and breathtakingly short. Its lifespan is measured not in billions, but in a few fleeting millions of years. Every second of its existence is a declaration of war against the single most powerful and patient force in the cosmos, gravity. The star's weapon in this war is nuclear fusion. Deep within its core, the pressures and temperatures are so extreme they beggar belief. We're talking hundreds of millions of degrees, a furnace so intense that atoms themselves are stripped down and forced together. The star begins its life by taking the most abundant element in the universe, hydrogen, and smashing its nuclei together to create helium. Each time this reaction occurs, a tiny amount of matter is converted into a colossal amount of energy, according to Einstein's famous equation, E=mc². This energy, in the form of radiation and heat, pushes outwards. This outward pressure is the only thing holding the star up. It's a constant, furious defiance against the star's own immense mass, which is relentlessly trying to crush it into a single point. For millions of years, the star exists in a state of delicate, violent equilibrium. Gravity pulls in, fusion pushes out. This balance defines the star, giving it its shape, its size, and its power. But even a titan can't fight forever. The very process that gives the star its life is also sealing its doom. The fusion furnace is a ravenous engine, and its fuel is finite. The star's core is a battlefield, and gravity is an enemy that never sleeps, never tires, and only needs one moment of weakness to claim victory. The story of how spacetime snaps begins here, not with a bang, but with a slow, inexorable countdown, as the greatest engine in the universe begins to run out of fuel. The star has burned brightly, a king in its cosmic domain, but its reign is coming to an end. And its death will be unlike anything else in the universe. It won't be a quiet fading into the night. It will be a cataclysm that rewrites the rules of space and time themselves. The beginning of the end, the Iron Crisis. For millions of years, our hypergiant has been a master of alchemy. It has spent its life turning the simplest element, hydrogen, into helium. But eventually, the unthinkable happens. The hydrogen in the star's core, the primary fuel for its entire life, begins to run out. The fires of fusion that have held gravity at bay for an age start to sputter. With the outward pressure weakening, gravity immediately seizes its advantage. The core, now composed mainly of helium ash, begins to contract. But the star isn't defeated yet. As the core shrinks, the pressure and temperature skyrocket to new, even more hellish levels. It becomes so hot and dense that a new, more powerful form of fusion ignites. The star begins to fuse the helium atoms themselves, forging them into carbon. A temporary reprieve. The new wave of energy pushes back against gravity, and the star finds a new equilibrium. But this is a desperate, short-lived victory. The fusion of helium releases less energy than the fusion of hydrogen, and it burns through its fuel supply much faster. The star has bought itself time, but the clock is ticking faster now. On the outside, the star swells dramatically, transforming into a red hypergiant. Its outer layers cool and expand, but its core becomes a frantic, multi-layered factory. As the helium in the very center is exhausted, the carbon core contracts again, heating up until it, too, ignites. The star begins fusing carbon into neon. Around this furiously burning carbon core, a shell of helium is still fusing into carbon. And around that, a shell of hydrogen is still fusing into helium. The star now resembles a colossal cosmic onion, with concentric shells of different elements all undergoing fusion simultaneously. After carbon comes neon, which fuses into oxygen. Then oxygen fuses into silicon. Each stage of this fusion ladder is a frantic, losing battle against gravity. Each new element it forges is heavier, and the energy returned from its fusion is less. The star is climbing a staircase where each step is shorter and burns away faster. The timeline of this process is terrifying. The initial hydrogen burning phase lasted for millions of years. The helium burning phase lasts for a few 100,000. The carbon burning phase? Just a few centuries. Neon burns for about a year. Oxygen for a few months. And the final stage, the fusion of silicon into iron, lasts for less than a single day. For one final, frantic day, the star is a flurry of activity, its core a churning maelstrom of creation. But at the end of that day, the core is filled with iron. And with iron, the star's long war against gravity comes to a sudden, catastrophic end. Iron is the ultimate cosmic ash. It is one of the most stable elements in the universe. Every fusion reaction up to this point, from hydrogen to silicon, has released energy. But fusing iron nuclei does not release energy, it consumes it. Iron is a fire extinguisher for stars. When the core fills with iron, the furnace doesn't just run out of fuel, it goes out. Instantly. In a fraction of a second, the energy generation that supported the weight of countless tons of matter simply stops. The outward pressure vanishes. There is nothing left to fight back. Gravity, the patient, relentless force that has been squeezing this star for its entire life, now faces no opposition. The star has reached the end of the line. For millions of years, it held its own. But now, in a silent, terrifying moment, gravity wins. And its victory is absolute. The core, and the universe around it, is about to be broken. The collapse, spacetime's final second. The moment the iron core gives way, the star dies. What took millions of years to build is undone in less than a second. This is not a slow, gentle process. It is one of the most violent and rapid events in the known universe. The core of the star, a sphere of super-dense matter roughly the size of the Earth, is now unsupported. The colossal weight of the star's outer layers, quadrillions upon quadrillions of tons of gas and plasma, comes crashing down. The core begins to collapse under this impossible burden. And it collapses fast. In less than a quarter of a second, the material of the core is falling inwards at speeds approaching 70,000 kilometers per second, nearly a quarter of the speed of light. As the core implodes, the iron nuclei are smashed together with unimaginable force. The very structure of matter is obliterated. Protons and electrons are crushed together to form a sea of pure neutrons, packed so tightly that a teaspoon of this material would weigh more than all of humanity combined. The entire core, once the size of a planet, shrinks down to a ball of neutron degenerate matter no larger than a city. In an instant, this new, ultra-dense neutron core becomes incompressible. It is as if the collapsing matter has hit a solid wall. The implosion halts, and all that infalling kinetic energy has to go somewhere. The result is a titanic recoil, a shockwave of monumental proportions known as the core bounce. This shockwave begins to blast outwards, back through the torrent of material still falling inwards. It carries with it an incredible amount of energy, but on its own, it's not enough. The infalling matter is too dense, and the shockwave begins to stall, threatening to fizzle out. But something else was created during the collapse: neutrinos. As the protons and electrons were forced together, a ghostly flood of these nearly massless particles was unleashed. For a few brief seconds, the dying star radiates more energy in the form of neutrinos than all the other stars in the observable universe combined. These neutrinos, normally so aloof that they can pass through an entire planet without interacting, are now so numerous that they slam into the material behind the stalled shockwave, re-energizing it with a colossal push. The revitalized shockwave explodes outwards with renewed fury. It tears through the star's outer layers, heating them to billions of degrees. This is the moment the star detonates as a Type II supernova. The resulting explosion is an event of almost unimaginable brilliance. For a few weeks, the single dying star will outshine its entire host galaxy of hundreds of billions of other stars. It will release more energy in an instant than our Sun will in its entire 10 billion year lifetime. The elements forged in the heart of the star, and even heavier elements created in the searing heat of the explosion itself, are blasted out into the cosmos. The carbon in our cells, the oxygen we breathe, the iron in our blood, all were created in the hearts of stars like this one and scattered by their explosive deaths. We are, in the most literal sense, made of stardust. But for a star as massive as our hypergiant, even this cosmic spectacle is just a sideshow. While the outer layers are erupting into a supernova, the core, the remnant left behind, is too massive to survive. The neutron degenerate matter, that ultra-dense ball of neutrons, cannot support its own weight. The force of gravity is so overwhelming that nothing, not even the fundamental forces that keep atoms from collapsing, can stand against it. The core collapse continues. There is no known force in the universe to stop it. The matter crushes down, smaller and smaller, beyond the size of a city, beyond the size of a mountain, beyond the size of a pinhead. It collapses towards a point of zero volume and infinite density. And as it collapses, it does something profound. According to Einstein's theory of general relativity, mass doesn't just pull on things. It fundamentally warps the fabric of reality. It tells space-time how to curve. The mass of our Sun creates a gentle curve, like a bowling ball on a trampoline, guiding the planets in their orbits. But the mass of this collapsing core, squeezed into an infinitesimally small point, doesn't just curve spacetime. It breaks it. The funnel becomes infinitely deep. The fabric of reality is torn, and at the center of the dying star, a hole is punched through the universe itself. A black hole is born. The birth of a black hole. The supernova's light fades. The cosmic debris expands into a beautiful, glowing nebula. But at the heart of where the star once stood, there is now a wound in the universe. An object defined not by what it is, but by what it is not. A region of absolute absence. This is a black hole. But what does that truly mean? To understand it, we must first understand its most famous feature, the event horizon. The event horizon is not a physical surface. You can't touch it. It's not made of matter. It is a boundary, a one-way door in spacetime itself. It is the point of no return. Imagine a powerful river flowing towards a massive waterfall. Far upstream, the current is gentle. A strong swimmer can easily swim against it and escape to the shore. But as you get closer to the waterfall, the current gets stronger. At some point, you cross an invisible line where the water is flowing faster than even the strongest swimmer could ever hope to swim. Past this line, no matter how hard you struggle, the current will inevitably carry you over the edge. The event horizon is that line for gravity. It is the precise distance from the center of the black hole where the gravitational pull is so immense that the escape velocity, the speed you would need to escape its pull, becomes greater than the speed of light. And since nothing in the universe can travel faster than light, nothing that crosses the event horizon can ever get back out. It is the edge of a causal abyss. Information can pass in, but it can never pass out. The size of this event horizon is determined by the object's mass, a threshold known as the Schwarzschild radius. For an object with the mass of our Sun, the Schwarzschild radius is about 3 kilometers. For the collapsed core of our hypergiant, which might contain 5 or 10 times the mass of our Sun, the event horizon could be 15 or 30 kilometers across. All that mass, crushed into a point, is now hidden within this sphere of perfect blackness. From a safe distance, the black hole's gravity behaves just like any other massive object. If you replaced our Sun with a black hole of the same mass, the Earth and other planets would continue to orbit it just as they do now, though in a very cold, dark solar system. The extreme physics are confined to its immediate vicinity. But as you get closer, things get weird. This is where Einstein's general relativity really comes into play. The theory describes gravity not as a force, but as the curvature of a four-dimensional fabric called spacetime. Massive objects distort this fabric, and other objects simply follow the straightest possible path through this curved geometry. Around a star or a planet, this curvature is a gentle depression. Around a black hole, the depression becomes a bottomless pit. Spacetime flows into the black hole like water down a drain. And it doesn't just pull on space, it pulls on time. This is the phenomenon known as gravitational time dilation. The stronger the gravity, the slower time flows. This isn't a metaphor or a trick of perception. It's a fundamental property of the universe. Clocks in a strong gravitational field literally tick slower than clocks in a weak one. This has been experimentally verified. The GPS satellites orbiting Earth have to constantly adjust their clocks because time runs slightly faster for them in their higher orbit than it does for us on the surface. Near a black hole, this effect is taken to the absolute extreme. Imagine you are watching a brave astronaut fall toward the event horizon from a safe distance. As they get closer, you would see their clock begin to tick slower and slower compared to yours. Their movements would appear to slow down, as if they were moving through molasses. The light from their spaceship would become stretched to longer and longer wavelengths, shifting from blue to red, and then to infrared, and finally to radio waves, a process called gravitational redshift. As they reach the event horizon, from your perspective, something truly bizarre happens. Time for them would appear to stop completely. You would see them frozen at the edge of the black hole, their image getting dimmer and redder, stretched and smeared across the horizon over an infinite amount of time. You would never, ever see them cross. They would simply fade away into nothingness, a static ghost imprinted on the edge of spacetime. From the astronaut's perspective, however, nothing special happens at all. Their clock ticks normally. They feel no bump, see no wall. In their own frame of reference, they pass across the event horizon in a finite amount of time, blissfully unaware that they have just crossed the point of no return. The disconnect between these two experiences, the observer who sees time freeze and the traveler who experiences nothing, is one of the deepest and most profound paradoxes of black hole physics. The star is gone. In its place is a tear in the very fabric of existence, a place where our understanding of space, time, and reality itself begins to crumble. We're now standing at the edge of the abyss, a place where time itself behaves in ways we can barely comprehend. The journey from here only gets stranger. If you're enjoying this trip to the most extreme corners of the cosmos, and if you want to support explorations like this, please take a moment to subscribe and click the notification bell. It's a simple act that helps us continue to unravel the biggest mysteries of the universe. Now, let's take the plunge. Crossing the threshold, inside the abyss. So what happens after you cross the event horizon? For the outside universe, you're gone forever. No message, no light, no signal of any kind can escape the black hole's grasp and return to tell your story. But for you, the journey continues. The moment you cross the horizon, the fundamental nature of reality around you shifts. Outside the black hole, you are free to move in any direction in space, forward, backward, left, right, but you are relentlessly carried forward in one direction in time, towards the future. Inside the event horizon, these roles flip. Now, you are relentlessly carried forward in one direction in space, towards the center. The direction, inward, is no longer a choice, it is your future. Just as you cannot stop yourself from moving into tomorrow, you cannot stop yourself from moving towards the singularity. You could fire your spaceship's rockets with all the power in the universe, and it would accomplish nothing. You wouldn't slow down. You wouldn't reverse course. You'd simply be burning fuel on a one-way trip to the center of the abyss. Trying to move away from the singularity inside a black hole is like trying to move back to yesterday. It is a physical impossibility. The very fabric of space-time is flowing inward, faster than the speed of light, carrying you with it. For a truly colossal, supermassive black hole, the kind found at the center of galaxies. Crossing the event horizon might actually be quite peaceful. The curvature of spacetime at the horizon is relatively gentle, and you wouldn't feel any immediate discomfort. But our black hole was born from a hypergiant star. It's a stellar mass black hole, and for these smaller, denser objects, the experience is far more violent. Here, you would encounter a gruesome process known as spaghettification. The term might sound whimsical, but the reality is anything but. Tidal forces are the culprit. The force of gravity is not uniform, it gets stronger the closer you are to the source. As you fall feet first towards the black hole's center, the gravitational pull on your feet becomes exponentially stronger than the pull on your head. This difference in force would begin to stretch your body. At first, it would be a gentle tug, but it would rapidly intensify into an irresistible pull. You would be stretched longer and longer, like a piece of spaghetti. At the same time, the gravitational forces acting on your sides would be squeezing you inwards. Every part of your body is pulled towards the central point, so you'd be compressed from the sides while being stretched from top to bottom. Any object, whether it's an astronaut, a planet, or another star that gets too close, is ripped apart atom by these overwhelming tidal forces, forming a long, thin stream of matter that spirals down into the black hole. But let's imagine you could somehow survive this. What would you see? The view would be unlike anything else. Looking up, away from the singularity, the light from the entire external universe would be compressed into a shrinking, intensely bright, blue shifted circle. It would be like looking out of a fisheye lens that contains all of space and time. Through this window, you might, in principle, be able to see the entire future of the universe play out in fast forward as time outside speeds up relative to your own. Looking down towards the singularity, there would only be darkness. An absolute, perfect blackness, as no light can travel from the center outwards. You are trapped in a cone of spacetime that is collapsing around you, with your past universe visible through a shrinking window and your future a single, inevitable point of termination. The end of reality, the singularity. All paths inside a black hole lead to one place, the singularity. This is the final destination. It is the point where the collapsed core of the star now resides, a place where our current understanding of physics completely and utterly fails. According to general relativity, the singularity is a point of zero volume and infinite density. All the mass of the collapsed star, the equivalent of several suns, is crushed into a region smaller than an atom. Here, the curvature of spacetime, the very quantity that defines gravity, becomes infinite. The equations that have guided us so well through the cosmos produce answers that are nonsensical. The laws of physics break down. It is a true point where spacetime snaps. Concepts like space and time cease to have any meaning. The density, the pressure, the temperature, the curvature, they are all infinite. What does that actually mean? We don't know. It's the universe's version of a division by zero error. It signals that our theory, general relativity, is incomplete. It's a magnificent theory for describing the large-scale universe, but it can't handle the quantum realm of the infinitely small. To truly understand the singularity, we would need a unified theory of quantum gravity, a holy grail of modern physics that has eluded scientists for decades. Is the singularity truly a one-dimensional point? Perhaps not. Most real stars spin, and when a spinning star collapses, its angular momentum must be conserved. A single point cannot have rotation. Instead, the theory predicts that the singularity in a rotating black hole, known as a Kerr black hole, is smeared out into a ring of zero thickness but a finite radius. This ringularity is even stranger than a point singularity. The mathematics of a Kerr black hole suggests that it might be possible, in a purely theoretical sense, to pass through the center of the ring without hitting the singularity itself. This has led to wild speculation about these objects being gateways, or wormholes, to other universes or other points in our own spacetime. However, most physicists believe that the path to such a singularity would be incredibly unstable. The slightest perturbation would cause the gateway to collapse, ensuring nothing could ever actually pass through. It seems the universe has a way of protecting itself from such paradoxes, a concept known as the cosmic censorship hypothesis, which posits that all singularities must be clothed and hidden from view by an event horizon. So what really lies at the center? Is it a point of infinite madness? Or does quantum mechanics step in at the last moment to prevent this infinity? Some theories propose that the matter doesn't collapse to a single point but forms an ultra-compact object like a Planck star, which then rebounds in an incredibly slow-motion explosion over trillions of years. Other ideas, like string theory, suggest the singularity is replaced by a vibrating, multidimensional object called a fuzzball. For now, the heart of a black hole remains the greatest mystery in all of physics, locked away behind a perfect veil of spacetime. We have taken a journey from the heart of a colossal star, a cosmic titan burning hundreds of thousands of times brighter than our sun, to its dramatic and violent death. We witnessed its core collapse in a fraction of a second, triggering a supernova that seeded the cosmos with the building blocks of life. And from those ashes, we saw the birth of its monstrous successor, a hole in the fabric of reality itself. We have stood at the event horizon, the precipice where time slows to a stop for the outside world. We have crossed that threshold into a realm where space and time swap their roles, where all paths lead inexorably inward. And we have ended our journey at the singularity, a point of infinite density where our laws of physics break and reality as we know it ceases to exist. But the story doesn't quite end there. A profound question lingers, a ghost haunting the edge of the abyss. The laws of quantum mechanics insist that information can never be destroyed. Yet, a black hole seems to be the ultimate information shredder, taking in all the complex details of a star, its composition, its history, and seemingly erasing it, leaving behind only mass, spin, and charge. This is the black hole information paradox, a deep conflict between our two most fundamental theories of the universe. Stephen Hawking proposed that black holes are not entirely black. They slowly evaporate over immense timescales by emitting a faint thermal glow, now known as Hawking radiation. But this radiation appears to be random, carrying no information about what fell in. Does the information truly vanish, forcing us to rewrite the laws of physics? Or is it somehow encoded in the subtle quantum entanglement of the outgoing radiation, hidden in a way we don't yet understand? Recent theories suggest information might be preserved on the event horizon itself, like a cosmic hologram. The star is gone, spacetime is broken, but the information of what it once was might be encoded on the edge of that darkness, a final ghost in the machine. A black hole isn't just an object, it is a question mark hanging in the void, challenging everything we think we know and asking us, what are the ultimate limits of reality? The universe is filled with these incredible, awe-inspiring objects, and each one holds clues to the deepest secrets of our existence. If you want to continue exploring these mysteries with us, don't forget to subscribe. And share your thoughts in the comments below. What part of the black hole journey fascinates you the most? What if you rode a light beam into a black hole? Long before the first stars ignited, the rules of the universe were already being written. Physics was experimenting with reality. It conceived of objects with no mass, moving at a speed nothing could surpass. It imagined places where gravity becomes so strong that space and time themselves break down. This is a journey into those extremes. Not a myth, not a monster story, but a real exploration of physics, following a single particle of light into the heart of a black hole. It's a journey that stretches the idea of what reality can be, to a place where our understanding quietly ends. To follow this path, we must first grasp the strange and unfamiliar nature of our vessel. Welcome to the Sleepy Scientist. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near a city, a forest, or somewhere quiet in between, feel free to share where you're watching or listening from. Before we begin, we should appreciate the vehicle for this one-way trip. You are not just traveling fast. You're moving at c*, the cosmic speed limit. It's a fundamental constant of nature. Nothing with mass can ever reach this speed. As an object with mass accelerates, it requires more and more energy, with the final step to light speed requiring an infinite amount. But you are not made of matter. You are a photon, a fundamental particle of light, with no rest mass. You are pure energy, born moving at c and destined to end moving at c. This unique property leads to something extraordinary. According to Einstein's theory of relativity, the faster you move, the slower your time passes relative to a stationary observer. At the speed of light, this effect becomes absolute. From the perspective of the outside universe, a photon's clock is stopped. This means your journey across millions of light years is, for you, instantaneous. The distance contracts to nothing. This presents a quiet paradox. How can there be a story of final moments if the entire trip happens in no time at all? The answer lies in shifting our perspective. While for you, no time elapses, for the rest of us, your journey is very real. To tell your story, we must become that distant observer, watching your beam of light streak across the cosmos. We will narrate the moments you cannot experience, the forces you cannot feel, and the final, inevitable fate that awaits at the end of your path. Your journey begins far from the black hole, in the relative quiet of deep space. But even here, its presence is felt. A black hole is what remains when a massive star has collapsed under its own weight, compressing its matter into a region of enormous density. This doesn't just create a powerful gravitational pull. According to Einstein's theory of general relativity, it fundamentally warps the fabric of spacetime. If spacetime is a stretched sheet, a star creates a dimple. A black hole creates a seemingly bottomless well. As a beam of light, you must follow these curves in spacetime. This phenomenon is known as gravitational lensing. From your path, the universe begins to distort. The light from stars and galaxies behind the black hole is bent around it. You would see stars that should be hidden appear at its edges, their light smeared into arcs and rings. The entire sky of the distant universe becomes concentrated into a shrinking window. Closer in, a different spectacle appears. A swirling, incandescent disk of matter encircling the darkness. This is the accretion disk. It is a collection of gas, dust, and the remnants of stars that ventured too close and were torn apart. This material is trapped in a spiraling orbit. As it gets closer, it moves at incredible speeds, and the intense friction and compression heat it to millions of degrees, causing it to glow brighter than any star. This is why black holes, objects of pure darkness, are often the brightest sources of radiation in the universe. The light comes not from the black hole itself, but from this superheated matter in its final moments. You, as a beam of light, cut through this inferno of X-rays and gamma rays. Your path is direct. You are not matter to be caught in this orbital dance. You pass through the glowing, violent chaos. Below you now is only pure, perfect blackness. This is the edge of the abyss. You are approaching the event horizon. The event horizon is not a physical surface. You wouldn't feel it. It is a mathematical boundary, a one-way door in spacetime. An often used analogy is a river flowing towards a waterfall. Far away, you can move in any direction. But closer in, the current strengthens until it flows faster than you can swim. Once you cross that line, all paths lead over the edge. For a black hole, the current is the inward flow of spacetime itself, and the swimming speed is the speed of light. The event horizon is the point where the escape velocity exceeds the speed of light. Since nothing can travel faster, anything that crosses is trapped. For an observer watching from a safe distance, something strange would happen. From their perspective, you would never quite reach it. As your light fights to climb out of the deepening gravity well, it loses energy. This appears as a gravitational redshift. Your brilliant light would seem to turn red, then infrared, and eventually fade into radio waves of ever-decreasing energy. At the same time, they would see your time slow down, an effect called gravitational time dilation. Your progress would appear to grind to a halt. To the outside universe, you would seem frozen at the edge of the black hole, your image lingering for an eternity before fading from view. But this is only their perspective. For you, the journey continues. You are riding the current of space-time as it flows into the black hole at the speed of light. There is no pause. You cross the event horizon. The moment you pass this threshold, the universe is split in two. The outside world, which you can never return to, and the inside of the black hole, which you can never leave. You are now inside. The moment of crossing is uneventful. There is no wall, no jolt. But the consequences are absolute. The laws of physics have been twisted into a new and unfamiliar form. To understand what happens next, we must choose our black hole. A small, stellar mass black hole, just a few times the mass of our Sun, would be a very different destination from a supermassive one, which can be millions or billions of times more massive. The difference is crucial because of tidal forces. Near a black hole, the gravitational pull on the part of an object closer to the center is exponentially stronger than the pull on the part farther away. This difference stretches the object vertically while compressing it horizontally, a process known as spaghettification. If you were falling into a small black hole, these tidal forces would tear you apart long before you reached the event horizon. So, let's imagine you are aimed at a supermassive black hole. Because it is so much larger, the curvature of spacetime at its event horizon is much more gentle. The tidal forces are weaker. An astronaut could cross the event horizon of a supermassive black hole completely unharmed, unaware they had sealed their fate. You, as a point particle of light, are not subject to spaghettification in the same way, but by choosing a supermassive black hole, we allow for a journey to continue inside the event horizon. You have passed through the quiet, invisible gate. Your future now has only one possible destination. The moment you cross the event horizon, the roles of space and time are inverted. In the outside universe, you are free to move in any direction in space, but you are forced to move in one direction in time, forward. Inside the event horizon, this is flipped. The direction toward the center of the black hole, the singularity, is now your future. You are forced to move toward it just as inexorably as you were once forced to move into tomorrow. It is no longer a place in space, it is a moment in time. Trying to move away from the singularity would be like trying to travel back to yesterday. What would you see? The view of the outside universe would have compressed into an intensely blue shifted window that snaps shut as you cross. The entire history and future of the external universe flashes by. Looking back now would reveal only darkness. The event horizon is a moment in your past. Even though you crossed the horizon of our supermassive black hole safely, the threat of spaghettification was only postponed. As you continue inward, the distance to the singularity decreases, and the tidal forces grow exponentially. Any matter that fell in with you would now be unmade. It would be stretched into a thin filament of molecules, then atoms, then a stream of fundamental particles, all funneled down to the very end of space and time. You are being delivered to the singularity. Here, at the heart of the black hole, is where our story, and physics itself, ends. The singularity is the ultimate unknown. According to general relativity, it is a point of zero volume and infinite density, where the curvature of spacetime becomes infinite. It is a place where the equations that have guided us on this journey break down. They produce answers of infinity, which is a physicist's way of saying that the theory has reached its limit. Our other great theory of reality, quantum mechanics, also fails to provide a clear answer. This is where the infinitely large world of gravity meets the infinitely small world of quantum particles, and we do not yet have a theory of quantum gravity to describe what happens. What is it? Is it an infinitely sharp point? Some theories suggest it might be a quantum fuzz, where spacetime is a chaotic foam. Other, more speculative ideas propose it might be a gateway, a wormhole to another universe, or a Planck star that eventually rebounds. These are fascinating possibilities, but for now, they remain deep within the realm of speculation. For you, the beam of light, the journey is over. You have been absorbed into the point where space and time cease to have meaning. Or have you? Your journey seems like a definitive end. But quantum mechanics has a very strict rule. Information can never be destroyed. Information. Here is the unique quantum state of every particle that has ever fallen in. Quantum mechanics insists that this information must be preserved. If it's crushed out of existence at the singularity, this fundamental law is violated. This is the famous black hole information paradox. For decades, physicists wrestled with this contradiction. The most promising solution came from Stephen Hawking. In 1974, he showed that when quantum mechanics is applied near an event horizon, black holes are not completely black. They radiate. This Hawking radiation arises from virtual particles in empty space. Usually, these pairs of particles and antiparticles pop into existence and quickly annihilate each other. But at the edge of a black hole, one particle can fall in while its partner escapes, carrying energy away. This energy comes from the black hole's mass. Over immense timescales, this means black holes evaporate. So, does this solve the paradox? Hawking initially thought not, arguing the radiation was random and contained no information. However, he later changed his mind. The emerging consensus today is that the information must somehow be encoded in the outgoing radiation. Another idea, the holographic principle, suggests that all the information about the interior of a black hole is encoded on its two-dimensional event horizon, like a hologram. As the black hole evaporates, this information is imprinted onto the outgoing radiation. Your information isn't destroyed. It's scrambled and re-emitted over trillions of years. These are the frontiers of modern physics, where our most fundamental theories are pushed to their limits. They hint at a reality far stranger than we can imagine, where information is never lost, only transformed. So, what if you rode a light beam into a black hole? From your perspective, the journey is over before it begins. From an observer's perspective, you fade away at the edge of forever. And from the perspective of the universe itself, your physical form is annihilated, but the information of your existence is preserved, destined to be slowly radiated back out into the cosmos, a faint echo scattered across spacetime. Your journey is both an absolute end and a strange quantum transformation. It reminds us that at the edges of our understanding, the universe is not only stranger than we imagine, it is stranger than we can imagine. Black holes where information runs out of space. What if one of Stephen Hawking's most important discoveries was also, for a time, a profound mistake? A mistake that suggested the universe had a way of erasing things, a quiet process capable of deleting existence itself. We are going on a journey to the edge of a black hole, a place where the laws of physics seem to break down, and where information, the blueprint of our reality, appeared to vanish without a trace. This is the story of the black hole information paradox, a cosmic mystery that occupied Stephen Hawking for decades and continues to reshape our understanding of everything. It's a story that placed two pillars of modern physics in quiet opposition, forcing us to ask a difficult question: is our reality permanent, or can it be wiped clean? The answer, as we are now beginning to understand, is rewriting the rules of space and time. Welcome. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether it's late at night or early in the morning, feel free to share where you're watching or listening from. The birth of a monster. What is a black hole? Before we can explore the paradox, we need to understand the object at its center. What is a black hole? The name suggests a kind of cosmic emptiness, a region of darkness from which nothing, not even light, can escape. And that is not far from the truth. Imagine a star, one many times more massive than our Sun. For billions of years, it lives in a careful balance. The immense force of its own gravity, trying to crush it inward, is held off by the outward pressure of the nuclear reactions in its core. But stars, eventually, run out of fuel. When a truly massive star exhausts its furnace, that balance is broken. Gravity wins. In a final, quiet collapse, the star's core implodes under its own weight, compressing an enormous amount of matter into a point of almost impossible smallness. This point is called a singularity. It is a place where density and gravity become infinite, where our known laws of physics no longer seem to apply. Surrounding this singularity is a boundary, a line of no return known as the event horizon. Think of it like a river flowing toward a waterfall. As you get closer, the current grows stronger. Eventually, you cross a point where the water is moving faster than you could ever swim. No matter what you do, you are going over the edge. The event horizon is that point for spacetime itself. Once you cross it, the pull of gravity is so strong that you would need to travel faster than the speed of light to get away, something our universe does not allow. For a long time, physicists believed black holes were also remarkably simple. In the 1970s, the physicist John Wheeler noted that black holes have no hair. This idea became known as the no-hair theorem. It means that after a black hole forms, it forgets almost everything about what fell inside. It doesn't matter if it was a star made of gas, a planet made of rock, or a complex machine. Once it's gone, the only things that remain are the black hole's mass, its electric charge, and its spin. All the other details, all the hair, is hidden away behind the event horizon. Imagine two books, each with the same mass. One is a copy of Shakespeare's Hamlet, filled with complex information. The other is a book of blank pages. According to the no-hair theorem, if you were to throw both into identical black holes, an observer outside could not tell the difference. The two black holes would be indistinguishable. This simple elegance was a core part of black hole physics. But it also held the seeds of a deep crisis, a paradox that would be brought to light by the work of one of the great minds of the 20th century. Hawking's insight, the evaporating enigma. In the early 1970s, a young physicist named Stephen Hawking began to explore the strange place where two of our best theories of the universe meet. One was Einstein's theory of general relativity, which describes the world of the very large. The other was quantum mechanics, the strange and gentle rules that govern the world of the very small. It was a place few had thought to look. Black holes were seen as objects of pure relativity, eternal prisons for anything that fell in. Quantum mechanics, it was assumed, had little to do with them. Hawking showed that this assumption was wrong. He was studying how quantum fields behave near a black hole's event horizon. According to quantum mechanics, even empty space isn't truly empty. It is a quiet sea of virtual particles that constantly appear in pairs, a particle and an antiparticle, before quickly vanishing. They exist for such a short time that they are almost undetectable. But Hawking realized that if one of these pairs were to appear right at the edge of an event horizon, something remarkable could happen. It's possible for one particle of the pair to be pulled into the black hole, falling past the point of no return, while its partner escapes into space. To someone watching from far away, it would look as though the black hole itself was emitting a particle. This slow trickle of particles is what we now call Hawking radiation. But here is the important part. The particle that fell in had a kind of negative energy compared to the one that escaped. When it is swallowed, it quietly reduces the total mass and energy of the black hole. The implication was profound. Black holes are not eternal. They leak over unimaginable lengths of time, trillions of years for a sun-sized black hole, and much longer for larger ones. This steady emission of Hawking radiation causes the black hole to slowly lose mass, shrink, and, in the end, evaporate completely, vanishing in a final, quiet puff of radiation. This discovery was revolutionary. It was one of the first concrete predictions to come from the tentative joining of quantum mechanics and general relativity. It solidified Hawking's place as a titan of physics. But in solving one mystery, he had unknowingly created a much deeper one, a paradox that would trouble the foundations of his own work. The paradox takes shape: information annihilation. Hawking's discovery that black holes evaporate set the stage for a quiet crisis. Let us return to our two books. We have Hamlet, rich with information, and the blank book, with almost none. We drop them into a black hole. According to the no-hair theorem, the black hole forgets the details, remembering only mass, charge, and spin. For a while, physicists could accept this. The information wasn't gone, just hidden away forever inside the black hole. But Hawking radiation changed everything. If the black hole eventually disappears, what happens to the information it once held? Hawking's own calculations offered a startling answer. The radiation that escapes, he argued, is thermal. It's perfectly random, like a gentle hiss of static. Its properties depend only on the black hole's mass, not on what fell in. This means the radiation from the black hole that swallowed Hamlet and the one that swallowed the blank book would be identical. When both black holes finally vanish, all that's left is a generic cloud of radiation. There would be no trace of Shakespeare's masterpiece. The information it contained, its unique quantum state, would be gone from the universe. This might not sound like a crisis. We lose information all the time. When you burn a book, isn't the information lost? From a quantum perspective, the answer is no. If you could, in principle, collect every particle of smoke and ash, every bit of heat and light from the fire, you could reconstruct the original book. The information is still there, just scrambled. This idea, known as unitarity *, is a core principle of quantum mechanics. It says that information can change form, but it can never be truly lost. It is the rule that ensures the present state of the universe holds all the information about the past. Hawking's calculation showed a black hole breaking this fundamental law. It wasn't just scrambling information, it was deleting it from reality. This was the black hole information paradox. Physics was now in conflict with itself. General relativity predicted black holes, and when combined with quantum mechanics, those black holes seemed to be perfect information destroyers. But quantum mechanics, one of the most tested theories in science, insisted this was impossible. One of them had to be incomplete. This was not just a small puzzle. It suggested a breakdown in our description of reality, a world where the past could be truly erased. Something had to be wrong. The first battle lines, a deep disagreement. The idea that black holes could destroy information sent quiet shockwaves through physics. For Stephen Hawking, the conclusion felt logical. He was convinced that the unique nature of a black hole, where gravity is strong enough to tear spacetime, simply allowed the rules of quantum mechanics to be suspended. He believed the information was truly gone. He even made a famous bet with fellow physicists Kip Thorne and John Preskill, wagering that information was lost when a black hole evaporates. But many physicists could not accept this. For them, abandoning unitarity was too great a step. It would mean that quantum mechanics, the theory that so perfectly describes our world, was not fundamental. If information could be lost in a black hole, perhaps it could be lost elsewhere. The predictability of the universe was at stake. Leading the argument against Hawking's conclusion were physicists like Gerard T. Hooft and Leonard Susskind. They defended quantum mechanics and argued there must be a flaw in Hawking's reasoning. The problem, they believed, was not that quantum mechanics was wrong, but that our understanding of gravity was not yet complete. For decades, the debate continued. It was a quiet clash of ideas, pitting Hawking's deep insights into gravity against the firm foundations of quantum theory. The paradox became a driving force in the search for a theory of quantum gravity, a single theory that could finally unite the world of the very large with the world of the very small. The solutions they proposed were often as strange as the problem itself, pushing the limits of what we thought was real. The first of these ideas would suggest that our three-dimensional world might be little more than a projection. The holographic principle, a radical solution. As physicists wrestled with the information paradox, a strange and powerful idea began to form, led by Gerard T. Hooft and later developed by Leonard Susskind. It is called the holographic principle. The idea is a startling reimagining of what space and information are. It proposes that all the information inside a volume of space can be described by a theory that lives only on the boundary of that region. The common analogy is a hologram, the kind you might see on a credit card. It's a two-dimensional surface, but when you look at it, it produces a full three-dimensional image. All the information needed to make that 3D image is encoded on the 2D surface. The holographic principle suggests the universe itself might work this way. The three-dimensional world we see could be a projection of information stored on a distant, two-dimensional surface at the edge of the cosmos. How does this help with the paradox? It changes how we think about what happens when something falls into a black hole. According to the holographic principle, when our copy of Hamlet falls toward the black hole, its information does not actually cross the event horizon. Instead, its information gets imprinted on the two-dimensional surface of the event horizon itself. To an outside observer, the book's information, every quantum detail, is captured and stored on the horizon, like data on a vast, spherical surface. Now, when the black hole evaporates, the story changes. The Hawking radiation is no longer random. As the event horizon shrinks, the information encoded on its surface is subtly transferred to the escaping particles. The process is chaotic and complex, scrambling the information so that it looks random. But it is not lost. In principle, if you could collect every particle of Hawking radiation and perform an impossibly difficult decoding, you could reconstruct the book. The information escapes. Unitarity is preserved. The paradox appears to be solved. This holographic idea was a monumental step. It provided a framework where information was not destroyed. It was, however, more of a guiding principle than a precise mechanism, and it led to its own difficult questions. If one observer sees the information stored on the horizon, while another falling in carries it with them, where is the information really? This led to an even stranger problem, one that threatened to replace the point of no return with a wall of fire. Firewalls and fuzzballs, getting weirder. The holographic principle was a promising path, but as physicists looked closer, they found a new problem. In 2012, a group of physicists including Joseph Polchinski asked a difficult question. Their thought experiment, which became known as the firewall paradox, showed that the holographic solution might conflict with a key part of Einstein's theory of relativity. Here is the issue. For the information to escape, an outgoing particle of Hawking radiation must be connected, or entangled, with all the radiation that came before it. This is how the information is carried away. But we also know that when the particle was created at the horizon, it was entangled with its partner that fell into the black hole. This creates a problem. A fundamental rule of quantum mechanics says that a particle cannot be fully entangled with two different things at once. Something has to break. The physicists argued that the most likely thing to break was the entanglement between the particle that fell in and the one that escaped. But breaking that connection would release a tremendous amount of energy. The consequence would be that the event horizon is not the smooth, quiet place Einstein predicted. Instead, it would be a firewall, a searing hot membrane that would instantly destroy anything trying to cross it. This would violate one of the core principles of general relativity. And so, we were back to a deep conflict between our two best theories of the universe. This firewall problem led some physicists to even more radical ideas. One of the most interesting alternatives comes from string theory and is known as the fuzzball proposal. Championed by physicist Samir Mathur, this idea suggests that black holes are not what we think. There is no singularity, and there is no empty space behind an event horizon. Instead, a black hole is a giant, tangled ball of fundamental strings, a fuzzball. It has a physical surface, much like a star, but it is incredibly dense and strange. In the fuzzball picture, the information paradox simply goes away. When matter falls onto a fuzzball, it becomes part of the tangle of strings. The information is stored in the fuzzball's unique structure. And because there's no classical event horizon, there's nothing to stop information from getting out. The surface of the fuzzball radiates, much like a hot piece of coal, and that radiation naturally carries information about its structure. The idea is elegant, but it rests on string theory, which is not yet a proven theory. And so, while the debate continued, many felt there had to be an answer hidden in the mathematics, a clue that had been overlooked. That clue came in the form of a simple curve, first drawn by one of Hawking's own students. The Page curve, a glimmer of hope. While debates about firewalls and fuzzballs continued, a quieter, more mathematical approach was gaining attention. It began back in 1993 with Don Page, a physicist who had studied under Stephen Hawking. Page asked a simple but profound question. If information is saved, what should the amount of entanglement between the black hole and its radiation look like over time? This measurement is called entanglement entropy. Think of it as a measure of how much information is shared between the black hole and the radiation it has emitted. At the beginning, just after the black hole has formed, the entropy is zero. They share nothing. As the black hole begins to emit Hawking radiation, escaping particles are entangled with their partners inside. So, the entanglement between the black hole and the growing cloud of radiation begins to increase. Hawking's original calculation, which assumed information was lost, predicted that this entropy would just keep growing and growing, right until the black hole disappeared. At that point, you are left with a cloud of radiation that is highly entangled, but with nothing. The black hole it was connected to is gone. This is the paradox, expressed in mathematics. But Don Page argued that if information is conserved, something different must happen. The entanglement entropy should increase at first, but only up to a point. He calculated that this turning point, now called the Page time, happens when the black hole has evaporated to about half its original size. After the Page time, the entanglement entropy must start to decrease. This is because newly emitted radiation is now more entangled with the radiation that is already outside than it is with the shrinking black hole. The information is beginning to repeat itself in the radiation cloud. By the time the black hole vanishes, the entropy must fall all the way back to zero. This would mean the final radiation is a complete, self-contained system that holds all the information of whatever fell in. The graph of this process, entropy rising, then falling, creates a distinct shape, like an inverted V. This is the Page curve. For almost 30 years, the Page curve was a quiet beacon of hope. It was the precise mathematical signature physicists needed to find if they were to prove that information escapes. The problem was, no one knew how to derive this result from a theory of gravity. Every attempt using Einstein's theory just reproduced Hawking's original result: entropy rising forever. The Page curve was the answer, but the path to get there was missing. That is, until a revolutionary breakthrough in 2019 finally connected the pieces. The 2019 revolution, islands and wormholes. After decades of quiet disagreement, the breakthrough arrived in 2019 with a series of remarkable papers that changed the field. Physicists finally figured out how to calculate the page curve from a theory of gravity. The solution was as strange as it was elegant, involving ideas that sound like science fiction: space-time wormholes and hidden islands of information. The new calculations used a complex mathematical technique that, in simple terms, involves considering not just one universe, but many copies, or replicas, of it at once. What the physicists found was that the old calculations had been missing something. They had only considered the most obvious arrangement of spacetime. The new calculations revealed that at later times, after the page time, new and unusual spacetime geometries start to become important in the calculation. These new geometries are called replica wormholes. These are not wormholes you can travel through. They are mathematical, quantum connections that link the different replica universes in the calculation. And what they connect is what matters. These wormholes form a bridge between the interior of the black hole and the Hawking radiation that is now far away. This connection has a profound effect on the calculation of how much information is shared. It reveals that at late times, a part of the black hole's interior, a region now called an entanglement island, is, from an information perspective, no longer just part of the black hole. It is now considered part of the radiation's system. The information inside this island is no longer seen as trapped. Through the mathematics of the replica wormholes, it is now deeply connected to the radiation outside. When you include these new wormhole geometries in the calculation, the result is quiet and miraculous. In the early stages of evaporation, the old Hawking calculation is right, and the entropy rises. But after the page time, the replica wormhole geometries become the more important part of the calculation. Including the information from the entanglement island causes the total shared information to start decreasing. The calculation perfectly reproduces the page curve. This was a monumental achievement. It showed, for the first time, how a calculation based on our understanding of gravity could align with the quantum principle of information conservation. In the eyes of many physicists, the paradox was, in principle, solved. Information does get out, but the solution was not just a mathematical trick. It pointed toward a new picture of the universe, where the fabric of spacetime itself seems to be woven from the threads of quantum entanglement. What does this all mean? Rewriting reality. The successful calculation of the page curve is more than just a solution to a 50-year-old puzzle. It is a profound clue about the fundamental nature of reality. It suggests the relationship between gravity and quantum mechanics is deeper and stranger than we had imagined. The most important implication is that spacetime itself might not be fundamental. The island calculations suggest that the geometry of space is an emergent property, built from the connections of quantum entanglement. The wormholes that allow information to escape are not physical tunnels in a pre-existing space. In a sense, they are the space, representing the quantum connections between the black hole's interior and the distant radiation. This is powerful evidence for the holographic principle. It seems that gravity and the shape of space really can emerge from a lower-dimensional quantum system, just as a 3D hologram emerges from a 2D film. This breakthrough showed that Hawking's original calculation, while brilliant, was incomplete. He had missed the subtle quantum gravitational effects that become important late in a black hole's life. Appropriately, before his passing, Stephen Hawking himself seemed to change his mind. After conceding the bet he had made years earlier, his later work explored pathways by which information could escape, suggesting he no longer believed it was truly lost. The resolution of the paradox is now seen as a turning point in the search for a theory of quantum gravity. It provides a concrete mathematical place where general relativity and quantum mechanics can give a consistent answer. And yet, while we now have a story for that information gets out, the details of how it gets out are still unclear. The revolution of 2019 did not end the story. It opened a new chapter of even deeper questions. The lingering mysteries, the journey continues. We have arrived at a picture where information is saved, carried out of the black hole through mathematical wormholes connected to hidden islands. The paradox is resolved, in principle. But this, in principle, hides a world of unanswered questions. This is often how science works. A solution to one great puzzle reveals an even deeper layer of mystery. First, what is the physical process that encodes the information in the outgoing radiation? The replica wormhole calculation is a mathematical tool that gives us the right answer, but it doesn't describe the step-by-step physical events. How does the information from our copy of Hamlet get imprinted onto the escaping particles? Is it through a fuzzball-like surface, or some other process we have not yet imagined? Second, what does an observer falling into the black hole actually experience? The firewall paradox has not completely vanished. Reconciling the experience of the infalling observer with the outside observer who sees information escape is still a major challenge. We do not yet have a consensus on what an astronaut would see or feel. And what are entanglement islands physically? Are they actual regions of spacetime? The idea is speculative, but it is one that physicists are now exploring. These are the questions that now occupy the field. The information paradox pushed our theories to their breaking point, and in resolving it, we have been given a glimpse of a new, deeper layer of physics. The journey isn't over. It has transformed from a paradox into a roadmap, a guide for exploring the fundamental connections between gravity, spacetime, and information. Our journey has taken us from the fiery death of a star to the creation of an object that bends reality. We encountered Stephen Hawking's startling discovery that black holes die, and the deep paradox it created, a quiet conflict between the laws of gravity and the quantum world. We navigated a maze of strange solutions, from a universe that might be a hologram to black holes that might be giant balls of string. And finally, we arrived at the modern frontier, where mathematical wormholes and hidden islands of spacetime have shown a path forward, a way for information to escape, preserving the fundamental laws of quantum mechanics. The black hole information paradox is no longer seen as a sign that our theories are broken. It has become our most powerful tool. Black holes have changed from cosmic dead ends into theoretical laboratories, places where we can test the very limits of our understanding. They are the places where the next revolution in physics is being shaped. They force us to ask the deepest questions. What is space? What is time? And what is the information that writes the story of our universe? The quest to understand these cosmic enigmas is a quest to decode the source code of reality itself. And the secrets they have yet to reveal are only just beginning to unfold. The mistake that made Stephen Hawking famous. There are moments in the history of science that feel less like a sudden discovery, and more like a quiet correction. A single, deeply held idea must give way to a stranger one, and in that shift, our understanding of the universe changes. This is the story of such a moment, centered on the most famous physicist of our time. It is a story about a mistake Stephen Hawking would later call his greatest. It began with an idea that was simple, elegant, and deeply wrong: that black holes were perfect and eternal prisons. And it ended with a revelation that reshaped physics. A revelation that these cosmic voids are not entirely black. They glow. And in that faint glow, we find some of the deepest questions that science is still exploring today. The story begins in the early 1970s. The world of physics was fascinated by black holes, the strange prediction of Einstein's theory of general relativity. Imagine a star so large that it collapses under its own gravity, becoming an infinitely dense point. This point creates a gravitational field so strong that nothing, not even light, can escape once it crosses a boundary known as the event horizon. It is a one-way door in the fabric of spacetime. At the forefront of this work was a young physicist at Cambridge University, Stephen Hawking. He was a champion of an idea about black holes known as the no-hair theorem. The theorem was deceptively simple. It proposed that once a black hole forms, it loses almost all of its history. It does not matter what falls in, a star, a planet, a library of books. The black hole is defined by only three properties: its mass, its electric charge, and its spin. That is all. No other hair or features remain to tell you what it was made of. It is a featureless, empty, and simple object. This idea of a perfect cosmic prison was elegant. But it also created a serious problem, one that seemed to break one of the most sacred laws of physics, the second law of thermodynamics. At its core, the second law of thermodynamics is a law about disorder. It says that in any closed system, the total amount of entropy, a measure of randomness or chaos, will always increase over time. An intact egg is an ordered system. If you drop it, it becomes a disordered mess. You will never see that mess spontaneously reassemble itself into a perfect egg. The universe, according to the second law, moves from order to disorder. Entropy always goes up. Now, consider a black hole. Imagine you have a hot cup of coffee, full of the chaotic, fast-moving molecules that give it entropy. If you throw that cup of coffee into a black hole, something strange happens. According to the no-hair theorem that Hawking defended, the black hole swallows the coffee. The information about every chaotic molecule vanishes. The black hole's mass increases, but it remains a simple, hairless object. From the outside, it looks as though the entropy of the coffee has been erased from the universe. The total disorder of the cosmos has seemingly decreased. This presented a quiet crisis. It seemed that black holes could ignore one of the most fundamental rules of the cosmos. The universe's bookkeeping seemed to be broken, and black holes were the reason. This is where the story takes its first turn, not with a celebrated giant of physics, but with a young graduate student who dared to look at the problem from a different perspective. A challenger who saw not a violation, but a clue. His name was Jacob Bekenstein. In the early 1970s, Bekenstein was a PhD student at Princeton. While others wrestled with the idea that black holes were destroying entropy, Bekenstein had a thought that was both simple and radical. He was struck by a property of black holes that Hawking himself had helped prove, the area theorem. This theorem states that the surface area of a black hole's event horizon can never decrease. It can get bigger, or it can stay the same, but it can never get smaller. Bekenstein noticed a quiet parallel. 1. The entropy of the universe can only ever increase or stay the same. 2. The surface area of a black hole's event horizon can only ever increase or stay the same. The similarity was too neat to be a coincidence. Bekenstein made a bold suggestion. What if they were, in some deep way, the same thing? What if the entropy of a black hole is its surface area? This was a revolutionary idea. It meant that entropy was not lost when something fell into a black hole. It was simply absorbed and stored on the black hole's two-dimensional surface. The information about that cup of coffee was not erased, it was encoded onto the event horizon itself. This beautifully solved the paradox. When the coffee falls in, its own entropy disappears, but the black hole's mass increases, which in turn increases the area of its event horizon. The increase in the black hole's entropy would be more than enough to compensate for the entropy that was lost. The second law was saved. But the physics community was skeptical, and the most prominent critic was Stephen Hawking. Hawking thought Bekenstein's idea was a flawed analogy. His argument was a classic reductio ad absurdum. It went like this: if a black hole has entropy, as Bekenstein suggested, Then according to the laws of thermodynamics, it must also have a temperature. And anything with a temperature must radiate energy. It must glow. But black holes, by their very definition, were black. Nothing could escape. To suggest they could radiate was, to Hawking, absurd. It violated the very concept of what a black hole was. He was certain Bekenstein was wrong, and he set out to prove it mathematically. Stephen Hawking did not just disagree with Bekenstein's idea. He felt it mixed two separate parts of physics in a way that was not careful. General relativity, Einstein's theory of gravity, describes the world of the very large. Thermodynamics describes the world of the very small, the dance of atoms and molecules. Bekenstein was combining them, and Hawking was convinced this was a mistake. So, in late 1973, he began a calculation to settle the question. He wanted to analyze how matter behaves at the very edge of a black hole and prove that nothing could leak out. To do this, he had to use a third branch of physics, quantum mechanics. Specifically, he applied the principles of quantum field theory to the space around a black hole. At the heart of this theory is an idea that changes our intuition about empty space. According to quantum mechanics, a vacuum is not empty at all. It is a quiet flicker of energy, from which pairs of virtual particles are constantly appearing. A particle and its antiparticle come into existence for a fraction of a second, before finding each other and vanishing. This happens everywhere, all the time. Hawking's plan was to study this quantum dance at the edge of a black hole. He expected the intense gravity would have some effect, but he was sure it would not allow particles to escape. The calculations were famously difficult, an attempt to merge general relativity and quantum theory in a way no one had done before. He worked for months, expecting the equations to give him a simple answer: 0. The emission rate from a black hole should be 0. But the universe had a surprise waiting for him. The equations were not leading him where he thought they would. He checked his work again and again, sure he had made a mistake. But the result would not go away. The result was not 0. To his own quiet astonishment, Stephen Hawking's calculations showed that black holes do radiate. In his effort to prove Bekenstein wrong, he had accidentally uncovered the very mechanism that proved Bekenstein was right. It was a moment of profound intellectual reversal. The mechanism he found was strange and elegant. When a pair of virtual particles appears at the event horizon, something unusual can happen. Imagine one particle of the pair forms just inside the event horizon, while its partner forms just outside. The one inside is trapped, but its partner is free. With its twin gone, it can no longer annihilate. It escapes into space. To a distant observer, it would look as if the black hole had just emitted a particle. It would appear to be glowing. But this created another puzzle. The escaping particle carries positive energy away with it. To balance the universe's energy books, the particle that fell in must have had negative energy. When this negative energy particle falls into the black hole, it reduces the black hole's total mass. According to Einstein's equation, E equals mc squared, mass and energy are equivalent. So, by emitting a particle, the black hole loses mass. This was the revelation. Black holes are not eternal. They slowly leak energy and mass back into the universe. Over unimaginably long periods, they evaporate. A black hole the mass of our Sun would take far longer than the current age of the universe to disappear, but not an infinite amount of time. The smaller the black hole, the hotter it is, and the faster it evaporates. Hawking had set out to debunk Bekenstein, not prove him right. The final step came when Hawking used his newfound temperature to calculate the black hole's entropy. The equation he derived was precisely what Bekenstein had proposed, only now with an exact mathematical value. The entropy of a black hole was, definitively, proportional to the area of its event horizon. Hawking conceded. Bekenstein had been right. The mistake was not in Hawking's math. The mistake was his conviction that black holes had to be simple and eternal. By trying to prove a rival wrong, he was pushed into his most famous discovery. This glow was named Hawking radiation. And in admitting his error, Hawking had inadvertently created a new mystery, one even deeper than the last. The discovery of Hawking radiation was a beautiful synthesis of physics. But as scientists studied it, a new and unsettling problem emerged. This was the black hole information paradox, a puzzle that has guided physics for nearly 50 years. The paradox comes from another fundamental rule of physics, this time from quantum mechanics. This rule states that information, in a quantum sense, can never be created or destroyed. It can be scrambled or rearranged, but it is never truly gone. If you burn a book, the information in it is not lost. It is just transformed into a complex arrangement of ash, smoke, and heat. In theory, you could track every particle and reconstruct the original text. Now, we return to our black hole. We throw a book into it. The information contained in that book falls past the event horizon. For a while, this is not a problem. The information is inside the black hole. But then, the black hole begins to evaporate through Hawking radiation. And here is the paradox. According to Hawking's original 1974 calculation, the radiation that comes out is random. It carries energy, but no information about what fell in. A black hole made from a star would radiate in exactly the same way as a black hole made from a library. So, what happens when the black hole evaporates completely? It vanishes in a final puff of random radiation. Where did the information from the book go? It cannot be in the black hole, because there is no black hole left. It cannot be in the radiation, because the radiation is random. It seems the information has been erased from the universe. This is a profound violation of quantum mechanics. It places general relativity and quantum mechanics in quiet opposition to each other. Hawking's mistake did not just show that black holes glow. It used that glow to reveal one of the deepest cracks in the foundations of modern physics. If this kind of calm exploration into the mysteries of the cosmos helps you find a sense of wonder, consider subscribing to the channel. That way, you will not miss our next journey to the edge of what we know, as we explore the quiet and beautiful puzzles of our universe. For 30 years, Stephen Hawking was the strongest defender of the idea that information was destroyed. He made a famous bet in 1997 with physicists John Preskill and Kip Thorne, arguing that information was lost forever. But as evidence from other areas of physics began to build, his confidence started to shift. In 2004, at a conference in Dublin, he stood before his colleagues and announced that he had been wrong. Information, he conceded, was not lost. He paid off his bet to Preskill with a baseball encyclopedia, a symbol of information's ability to be stored and retrieved. But how does the information get out? That question is still being debated, and the search for an answer has led to one of the strangest ideas in all of science, the holographic principle. This idea grew directly from the work of Einstein and Hawking. Remember that the information a black hole can hold is related to its two-dimensional surface area, not its three-dimensional volume. This is a surprising result. We are used to thinking that the amount of space inside a container determines how much it can hold. But for black holes, this is not true. It is as if all the information about the things that fell inside is stored on the two-dimensional event horizon. In the 1990s, physicists Gerard 't Hooft and Leonard Susskind proposed that this might be a fundamental principle of the entire universe. The holographic principle suggests that the reality we perceive, our three-dimensional world, could be a holographic projection of information happening on a distant, two-dimensional surface. This idea, which sounds like something from science fiction, is now a serious tool in theoretical physics. It suggests that when a book falls into a black hole, its information is not lost inside. It is scrambled and encoded on the event horizon. As the black hole evaporates, the Hawking radiation is not truly random. It subtly carries that information away, particle by particle, in a cosmic code we are only just beginning to understand. The story of Stephen Hawking and his most famous discovery is a powerful reminder of how science truly works. It is not a straight line of inevitable genius, but a messy, human journey of curiosity, disagreement, and the courage to change one's mind. We began with a simple picture of black holes as perfect voids. But a bold question from a young physicist planted a seed of doubt. It was a radical idea that these prisons had a memory. In his quest to prove that idea wrong, Hawking was forced to combine the physics of stars with the physics of atoms. In doing so, he made a discovery that contradicted his own beliefs. He found that black holes were not silent and black. They have a temperature. They glow. His greatest mistake was not an error in calculation, but an error in conviction. And in this spectacular intellectual reversal, he unveiled a far deeper mystery, the information paradox. The resolution to that paradox is still being written, but the path forward is lit by the glow from Hawking's discovery. It has led us to the edge of reality, to the mind-bending idea that our universe might be a grand hologram. Stephen Hawking is remembered as a genius who explored the deepest questions of existence. But his greatest contribution was not just in the answers he found. It was in the questions he raised. And it all started with the mistake that made him famous, a mistake that forced him, and us, to see that even the darkest, most absolute prisons in the universe have a light of their own. Black holes don't just die, they explode. In the quiet, deep spaces of the cosmos, there are structures. For a long time, they were seen as the universe's final punctuation mark, objects of such immense gravity that nothing, not even light, could move fast enough to pull away. For trillions of years, long after the last stars have faded, these entities, black holes, will likely remain. They will be the last large structures in a dark and expanding universe, quiet reminders of a more active time. They seem to be the very definition of permanence. Or so it was thought. It turns out these cosmic objects may not be immortal. They appear to carry a quiet vulnerability, a principle woven into the fabric of reality itself. And when their end comes, after an almost unimaginable stretch of time, they do not simply fade. They do not go quietly. After an eternity of slow evaporation, of losing its own mass back into the void, a black hole shrinks. It contracts from the size of a star system to the size of a planet, then a city, then a mountain, until it becomes an object of microscopic, quantum proportions. At that point, it becomes unstable. In its final moments, it is thought to release its entire remaining mass in a single, intense flash of energy. A burst of gamma rays brighter than anything the universe has seen since its earliest moments. This is not a story of fiction. It is the story of the death of a black hole. It begins not in the center of a collapsing star, but in the apparent emptiness of space itself. It is a story about energy, borrowed and repaid at the edge of oblivion, a process so subtle it remained hidden for almost all of human history. To understand how the universe's most perfect prison might be undone, we have to look at the edge of reality, where our understanding of the world begins to fray into a sea of quantum uncertainty. This is the story of Hawking radiation, and it describes one of the most profound events the universe may ever witness. The immortal titans. Before we can talk about a black hole's end, we should first understand its life, or rather, its seemingly eternal existence. For most of scientific history, a black hole was considered the end of the line. The final, irreversible state for matter. Imagine a star, many times more massive than our own sun. For millions of years, it exists in a state of balance. The outward pressure of nuclear fusion in its core pushes matter away, while the immense inward pull of its own gravity tries to draw everything together. But this balance cannot last forever. Stars, eventually, run out of fuel. When a truly massive star exhausts its core, the outward push stops. Gravity wins. In a fraction of a second, the star's core collapses in on itself. The outer layers of the star are thrown outward in one of the most spectacular events in the cosmos, a supernova. But what is left behind is the real point of interest. The core continues to collapse, crushing itself past any known limit of density until it becomes a point of infinite density, a singularity. A black hole is born. The defining feature of this new object is not the singularity itself, which stays hidden, but the boundary around it, the event horizon. This is not a physical surface you could touch. It is the point of no return. Anything that crosses it, light, planets, entire stars, is thought to be lost forever. The gravitational pull beyond the event horizon is so strong that the speed required to escape is greater than the speed of light. And since nothing we know of can travel faster than light, nothing gets out. This is what gave black holes their reputation for being eternal. They are cosmic objects that only seem to consume. They grow, they merge, they become more massive, but they were never thought to shrink. In the far future, in an era cosmologists call the black hole era, it was believed that these objects would be the last complex structures left. The universe would be a cold, dark void, populated only by these quiet gravitational relics. This picture of permanence was deeply ingrained in physics, a fundamental part of Einstein's theory of general relativity. For decades, no one seriously challenged it. A black hole was a trap with no exit. Information that fell in was gone. Mass that fell in only made the black hole bigger. It was simple, and it was elegant. And it appears to have been incomplete. The first crack in this wall of permanence came not from a telescope, but from the mind of a theoretical physicist who asked a simple question. What happens when you combine the physics of the very large, gravity, with the physics of the very small, quantum mechanics? That physicist was Stephen Hawking, and his answer would rewrite the fate of the universe. The crack in infinity. The shift in understanding began with a paradox. In the early 1970s, physics was guided by two separate frameworks. Einstein's general relativity, which describes the world of the large, and quantum mechanics, which describes the strange, probabilistic world of the very small. They both worked perfectly in their own domains, but they did not play well together. And nowhere was the conflict between them clearer than at the edge of a black hole. Stephen Hawking, thinking about this conflict, realized something that seemed impossible. According to the laws of thermodynamics, any object with a temperature must radiate energy. Yet, according to general relativity, nothing can escape a black hole. So, could a black hole have a temperature? It seemed like a contradiction. But Hawking showed that not only could a black hole have a temperature, it must. And if it has a temperature, it must radiate. To understand how, we have to look at the quantum world. Our common sense picture of empty space is that it is empty. A perfect void. But quantum mechanics suggests a different picture. The vacuum of space is not truly empty. It is filled with a quiet, constant hum of activity, sometimes called the quantum foam. Out of this foam, due to a principle known as Heisenberg's uncertainty principle, pairs of virtual particles are thought to be constantly emerging. For an incredibly brief moment, a particle and its antimatter counterpart, an electron and a positron, for example, can borrow a tiny amount of energy from the vacuum to exist. They exist on borrowed time, and in a fraction of a second, they must find each other, annihilate, and repay their energy debt. This happens everywhere, all the time. Normally, this process has no observable effect. The particles are virtual, because their existence is too fleeting to be seen directly. They are born together and vanish together, leaving no trace. They are part of a quantum accounting that always balances out to zero. But Stephen Hawking asked a critical question. What happens if this process occurs right at the edge of a black hole's event horizon? What if, in that fleeting moment, One of these virtual particles appears on one side of the point of no return, and its partner appears on the other? Suddenly, the situation changes. The pair can no longer find each other to annihilate. The rules that govern their existence are pulled apart by the black hole's extreme gravity. This is the crack in the armor of the immortal object. This is where the process begins. The cosmic heist. Picture the scene at the edge of a black hole. The event horizon marks the boundary. Spacetime itself is flowing into the black hole faster than the speed of light. It's like a cosmic waterfall. Right at this boundary, in the quantum foam, a pair of virtual particles flashes into existence. Let's call them particle A and particle B. They're linked, and destined to annihilate each other almost instantly. But in this location, their fate is altered. Imagine particle A, by chance, comes into being just inside the event horizon. It is immediately caught in the flow of space-time and falls toward the singularity. There is no escape, but its partner, particle B, appears just outside the event horizon. It is on the edge, but it is not yet lost. It has a chance to be flung away, escaping into the wider universe. This is where Hawking's insight becomes important. The universe is a good bookkeeper, it doesn't tolerate unpaid debts. The particle pair had borrowed energy to exist. Since they can no longer annihilate to repay it, the black hole itself must cover the cost. To explain this, physicists use the concept of negative energy. When particle B escapes, it becomes a real particle, carrying positive energy away into space. To balance the cosmic books, the particle that fell into the black hole, particle A, is considered to have negative energy from the perspective of a distant observer. When this negative energy particle is absorbed by the black hole, it subtracts from the black hole's total mass energy. It's as if you were to eat something with negative calories, you would lose weight. Every time a particle escapes, the black hole pays the price. It gives up a tiny piece of its own mass to turn the escaping, virtual, particle into a real one. This stream of escaping particles is Hawking radiation. To a distant observer, it appears as if the black hole itself is faintly glowing, emitting thermal radiation like a warm piece of coal. This is why black holes have a temperature. The radiation is real, and the energy it carries away is taken directly from the mass of the black hole. Now, we should be clear about the scale of this process. It is the slowest, most patient process in the cosmos. For a black hole with the mass of our Sun, the amount of energy it loses is minuscule. The power radiated is so low, around 10 to the power of -28 watts, that describing it as a certain number of particles per year can be misleading. Its temperature is a mere 60 billionths of a degree above absolute zero, far colder than the background temperature of space itself. This means that for now, all known black holes are actually gaining more mass from the leftover warmth of the Big Bang, the cosmic microwave background, than they are losing through Hawking radiation. They are still growing, but the universe is expanding and cooling. In the distant future, the background temperature will drop. There will come a time when the universe is colder than the black holes themselves. The feeding will stop, and in the cold darkness of the far future, the slow drip of Hawking radiation will become a one-way street. The titans will begin to waste away. The long, slow twilight. The process of a black hole's evaporation unfolds over truly mind-bending timescales. To say it takes a long time is a significant understatement. The numbers involved are so large they are hard to comprehend, making the 13.8 billion year age of our universe feel like a brief moment. Let's consider a black hole with the same mass as our Sun. Right now, it is absorbing more energy than it radiates. But let's fast forward to a time when the last star has burned out. This is the black hole era. In this cold, empty future, the universe's temperature will finally drop below the tiny temperature of a solar mass black hole. Only then will its evaporation truly begin. From that point, for that single solar mass black hole to completely evaporate, it will take roughly 10 to the power of 67 years. That is a 1 followed by 67 zeros. There is no easy analogy for this number. Now consider a supermassive black hole, like Sagittarius A*, the 4 million solar mass object at the center of our galaxy. Because a black hole's temperature is inversely proportional to its mass, Sagittarius A is much colder than a solar mass black hole. Its rate of evaporation is therefore incredibly slower. For it to evaporate, we would have to wait an estimated 10 to the power of 87 years. For the truly giant black holes at the centers of galaxy clusters, the time stretches to 10 to the power of 100 years, a number known as a googol. This is the long, slow twilight. For an eternity, the universe will be dominated by these slowly dying objects. They will shrink with a patience that makes geology look frantic. Their mass will be converted, particle by particle, into a diffuse cloud of low-energy radiation. But this is not the whole story. The relationship between mass and temperature is key to the final chapter. The rule is simple. The smaller the black hole, the hotter it is, and the faster it evaporates. This is where the story shifts from a slow, cosmic side to a sudden, final burst. If this kind of calm exploration into the world of physics helps you unwind, consider liking the video and subscribing to the channel. We dive into the deep mysteries of the universe every week. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. The fuse is lit. The slow evaporation of a massive black hole is only half the story. The more dramatic part lies in the relationship between a black hole's mass and its temperature. As a black hole radiates away mass, it shrinks. As it shrinks, its temperature increases. As its temperature increases, it radiates energy even faster. This creates a runaway feedback loop. The process accelerates. Let's follow a black hole on this final path. For trillions of years, it has been shrinking at an imperceptible rate. But as its mass dwindles, the pace quickens. What was once the size of a solar system eventually shrinks to the size of a planet. As it continues to shrink, its temperature skyrockets. By the time our black hole has dwindled to the mass of a large asteroid, it would be glowing with a visible, dull red heat. As it sheds more mass and shrinks to the mass of a mountain, its temperature would soar to millions of degrees, blazing with the light of a small star. The radiation it emits is no longer just a few low-energy particles. It's a torrent of high-energy photons, neutrinos, and other particles. The black hole is now a furnace, converting its mass into energy at a furious rate. This raises an interesting possibility. While large black holes formed from stars will only reach this stage in the far future, is it possible that smaller black holes already exist? Cosmologists theorize that in the ultra-dense conditions of the first moments after the Big Bang, tiny fluctuations could have crushed pockets of matter directly into black holes. These are known as primordial black holes. These primordial black holes could have formed with a range of masses. Many would have been so small they would have evaporated almost instantly. But, as Stephen Hawking calculated, a primordial black hole formed with the mass of a large mountain, about 1 billion tons, would have a lifetime roughly the current age of the universe. This is a remarkable thought. It means that ancient, tiny black holes could be reaching the final, explosive stages of their evaporation right now. Somewhere in space, a tiny black hole could be glowing, its mass disappearing in a runaway cascade. As it shrinks from the mass of a mountain to the mass of a car, then a bowling ball, the energy output becomes more and more extreme. In its final minutes, it would be emitting radiation at an incredible rate. The final moment is imminent. The final second. We now arrive at the end for our black hole. Billions or trillions of years of slow decline have all led to this, the final, catastrophic moment. In this last second, the black hole has shed almost all of its mass. It contains the remaining mass in a space far smaller than an atomic nucleus. The temperature soars to levels not seen since the first instant of the Big Bang. Here, the laws of physics as we know them, general relativity and quantum mechanics, must merge into a theory of quantum gravity that we do not yet have. What we can predict is that the runaway process of evaporation reaches its ultimate conclusion. As the mass approaches zero, the temperature and energy output approach infinity. In the last fraction of a second, the black hole is expected to release all of its remaining mass, perhaps several tons worth, in a single, definitive, and unimaginably energetic burst. This is the explosion. It is not an explosion of matter like a bomb. It is the pure conversion of mass into energy, following Einstein's equation, E=mc². The result is a flash of the highest energy radiation possible, gamma rays. The estimated energy released is monumental, equivalent to billions of powerful nuclear bombs detonating in the same point in space. For a fleeting moment, it would be one of the brightest points of light in the observable universe. After eons of being the universe's darkest objects, the black hole would die in a blaze of glory. After an existence defined by taking, it gives everything back. For years, this final explosion was just a prediction. The search for these events is now underway. Recently, neutrino detectors have recorded single, extremely high-energy particles arriving from space. For some of these, like a notable detection in 2023, there is no obvious astrophysical source, like an exploding star. This has led to speculation. One of the more intriguing, though unproven, explanations being considered by some research teams is that this lone particle could be a product of a dying primordial black hole. We may have already witnessed a faint echo of one of these cosmic events. The aftermath and the lingering mystery. What is left after the final flash? The answer is both simple and unsettling: nothing. Where there was once a point of immense density, there is now just an expanding sphere of radiation and particles, rapidly cooling and dispersing into the void. The black hole is gone. The mass it held has been converted back into fundamental particles and energy. The process of cosmic recycling appears to be complete. But this clean end leaves us with one of the deepest paradoxes in modern physics: the information paradox. According to quantum mechanics, information can never be truly destroyed. Information, in this context, is the unique quantum properties of every particle. The universe, at a fundamental level, should keep a record of its own history. If you burn a book, the information inside seems lost. But in principle, if you could collect every particle of ash, smoke, and heat, you could reconstruct the original book. The information is scrambled, but it's not gone. Hawking's original calculations, however, suggested that the radiation from a black hole is purely thermal. It contains no information about what fell in, other than its mass, charge, and spin. This would mean that if a black hole swallows an encyclopedia and then evaporates, the information within that encyclopedia is gone forever, violating a core principle of quantum physics. So, what happens to the memory of a black hole? Where does the information go? This is a question Stephen Hawking himself worked on for decades. He initially believed the information was lost, but later came to believe it must be preserved. Current theories are exploring several possibilities. One idea is that the information is subtly encoded in the outgoing Hawking radiation in a way we can't yet read. Another proposes that information is stored in a kind of quantum hair, faint fields that surround the event horizon. Some theories even speculate that the final moments could lead to the creation of a baby universe, with the lost information passed into a new reality. We do not have the final answer, but the death of a black hole forces us to confront this mystery. The explosion isn't just an end, it's a clue. It might be that in the final, fiery burst, the universe's secrets are not destroyed, but released. From cosmic titans seen as immortal, to slowly leaking relics, to microscopic bombs, our understanding of black holes has changed profoundly. They are not the eternal prisons we once imagined, but perhaps the universe's most patient transformers. They gather mass over eons, only to release it all in a final burst that seeds the cosmos with new energy. Their story shows the interplay between two great pillars of physics, gravity and the quantum world. It shows that even the most absolute rules can have subtle exceptions, and that the universe is often stranger than we imagine. Stephen Hawking once offered a piece of advice. He said, "So if you feel you are in a black hole, don't give up. There's a way out." He was speaking about the challenges of life, but his discovery gave that statement a literal, cosmic truth. It tells us that nothing, not even the most powerful objects in existence, seems to last forever. In the end, even the darkest corners of the universe may give way to a final, brilliant flash of light. The story of the cosmos is not one of eternal endings, but of endless new beginnings. Thank you for joining this journey to the end of a black hole. If you want to continue exploring the biggest questions in the universe, make sure to subscribe and check out our other videos. The cosmos is full of stories waiting to be told. The singularity, physics' ultimate error code. Every story we tell has a point where language falls short. Every map has an edge, a place where the known world gives way to the unknown. The universe, in its quiet and incomprehensible scale, seems to have its own version of this. It is a place where our descriptions of reality no longer hold. Where space loses its meaning, where time appears to stop, and where every physical law we have ever discovered, from the slow waltz of galaxies to the brief existence of a single particle, becomes silent. This boundary isn't in a distant, imagined reality. It exists, quietly, at the center of every black hole. This is the story of the gravitational singularity. It is a story about a place where our understanding reaches its limit, a question that has shaped the course of physics for a century. And it is the story of the patient, continuing search for a new language to describe it, before it leaves our picture of the universe incomplete. The anatomy of a collapse. To understand this limit, we first have to understand the process that leads to it. Our story begins not with a sudden event, but with a slow, inevitable collapse. Imagine a star, many times more massive than our Sun, that has spent millions of years in a delicate balance. For its entire life, the outward force of nuclear fusion, pushing matter apart, has been held in check by the constant, inward pull of its own gravity. But this balance is temporary. All stars, eventually, run out of fuel. When the core of this giant star is exhausted, the outward pressure from fusion disappears. Gravity, the patient and ever-present force of the cosmos, finally becomes unopposed. There is nothing left to hold it back. The star's core begins to fall inward. The outer layers are cast off in a supernova, a final release of light that can briefly outshine its entire galaxy. But the core itself keeps collapsing. Gravity pulls it inward, compressing it with a force that is difficult to picture. The matter becomes so dense, and its gravity so strong, that it starts to rewrite the rules of the space around it. It bends the fabric of spacetime, digging a well so deep that a boundary forms. This boundary is not a physical surface. It is a line defined by geometry, a point of no return. We call it the event horizon. Think of spacetime as a gently flowing river. Far from the black hole, you can move in any direction. As you get closer, the current grows stronger. You have to work harder to move away. The event horizon is the edge of a waterfall. Once you cross it, the river of spacetime itself is flowing inward faster than light, the ultimate speed of the universe. No matter how you try, you can no longer move away. The only direction is down. Every possible path now points toward a single destination, the center. This is the setting for our cosmic question, a one-way threshold in the universe. But the true mystery is not the event horizon itself. It's what waits at the bottom of that waterfall, at the end of that final, inward journey. The point of infinity. Once something crosses the event horizon, its journey does not end in a simple, compressed ball of matter. According to the mathematics of Albert Einstein's general theory of relativity, the language that has so perfectly described gravity on cosmic scales, the collapse continues. All the mass of what was once a star, and everything that has fallen in since, keeps crushing down, smaller and smaller, until it is compressed into a region with zero volume. Zero volume. Not just small, but infinitesimally small. A point with no dimensions. And yet, within that non-existent point, there is a finite, often enormous, amount of mass. This leads to a state of infinite density. The curvature of spacetime, which is how we experience gravity, also becomes infinite. At this point, the equations of general relativity no longer provide meaningful answers. They return infinities, a result that has no place in the physical world. It's like asking a calculator to divide by zero. The calculation cannot be completed. Physics, as we know it, falls silent. This is the singularity. This is the place where our most trusted laws of nature seem to end. The story becomes more complex from here. Not all black holes are the same. A simple, non-rotating black hole, called a Schwarzschild black hole, has a singularity that is a single point in space. But in the real universe, most things spin. When a spinning star collapses, its rotation is preserved and amplified. This creates a rotating black hole, described by the work of the mathematician Roy Kerr. In a Kerr black hole, the singularity is not a point. The forces from its rapid spin cause it to spread out into a thin, one-dimensional ring. A circle of infinite density and zero thickness. Whether a point or a ring, the outcome is the same. General relativity, our best description of gravity, predicts a place where its own rules no longer apply. It leads us down a path that ends in a paradox, an infinity that seems to have no physical reality. It tells us where physics stops, but it cannot tell us what, if anything, comes next. This contradiction is one of the most profound puzzles in modern science. It tells us, very clearly, that our story of the universe is not yet complete. To find the missing pages, we should first meet the minds who discovered the question. The minds that found the limit. Every great question has its history, the thinkers who pieced together the clues. The mystery of the singularity was uncovered over a century by a series of physicists who were both the architects of our modern understanding of gravity and the first to see its limits. The first, of course, is Albert Einstein. In 1915, he published his general theory of relativity, a new story about gravity. It was no longer a mysterious force pulling objects together. Instead, Einstein showed that gravity is the result of mass and energy curving the four-dimensional fabric of spacetime. Objects simply follow these curves. The Earth orbits the Sun not because it is being pulled, but because it is moving through a valley in spacetime created by the Sun's mass. His equations became the new language for describing the cosmos. But hidden in that language was a difficult sentence. Just a few months later, a German physicist named Karl Schwarzschild found the first exact solution to Einstein's equations while serving on the Russian front in the First World War. He described the spacetime around a single, non-rotating sphere of mass. His solution was elegant, but it held something strange. At a certain distance from the center, what we now call the Schwarzschild radius, the math seemed to break down. It produced an infinity. At the time, most physicists, including Einstein, thought this was just a flaw in the coordinates, not a feature of reality. They believed that in a real collapsing star, some other physics would step in to prevent such a strange state from ever forming. The question remained quiet until the 1960s, when the British mathematical physicist Roger Penrose looked at it from a new perspective. He wondered what would happen in the messy reality of a real dying star, not a perfect, idealized sphere. Using new mathematical tools, Penrose showed something remarkable in a 1965 paper. He proved that if an event horizon forms, the creation of a singularity was not just possible, but inevitable according to general relativity. It didn't matter if the star was asymmetrical or spinning. Once a boundary forms from which light cannot escape, the collapse to a singularity was a foregone conclusion. Penrose's work turned the singularity from a mathematical curiosity into a direct and serious prediction of Einstein's theory. For this insight, he was awarded the Nobel Prize in Physics in 2020. Working with Penrose, Stephen Hawking applied these same ideas not to the end of a star, but to the beginning of the universe. He showed that if you run the clock backwards, the expanding universe must have begun from a singularity as well, the Big Bang. Together, the Penrose-Hawking singularity theorems suggested that singularities were a fundamental part of our universe as described by general relativity, appearing at both the beginning of time and at the end of matter. But Hawking did not stop there. He would spend his life studying the nature of the event horizon, and in doing so, uncover a second, equally profound mystery that grew directly out of the existence of the singularity: a deep conflict between the world of gravity and the world of quantum mechanics. These four thinkers, Einstein, Schwarzschild, Penrose, and Hawking, brought us to the edge of the map. They showed us where our descriptions of the world break down. The next step was to explore the strangeness itself, to understand the physics of the journey toward that final limit. A journey where spacetime changes. Imagine you are an observer on a journey across the event horizon. Looking back, you can still see the universe you left, but it is a one-way view. No signal you send can ever return. You are now in the domain of the singularity, and the rules of reality have changed in a fundamental way. The journey inward reveals a physics that is deeply unfamiliar. The first change is a quiet restructuring of space and time. In our familiar world, we have three dimensions of space: up and down, left and right, forward and backward, and one dimension of time. We are free to move in any direction in space, but not in time. Time moves forward. You are always traveling into your future. Physicists visualize this with a concept called a light cone. Every possible future path you can take is contained within this cone, which points forward in time. As you approach a black hole, its gravity begins to warp spacetime, and this tilts your light cone inward, toward the black hole's center. The moment you cross the event horizon, something profound happens. Your future light cone tilts so completely that the entire cone, every possible future available to you, now points directly at the singularity. This is where the exchange happens. The spatial dimension pointing toward the singularity now behaves like time. Just as you cannot avoid moving toward next week, you can no longer avoid moving toward the singularity. It is no longer a place in space, it has become your future. At the same time, the dimension of time has taken on the character of space. You could, in theory, move within this new dimension, but all paths still end at the same inevitable future: the singularity. This inevitability is the next part of the journey. Trying to avoid the singularity once inside the event horizon is like trying to avoid a future date. You can do many things between now and then, but the date will arrive. The singularity is an appointment written into the very geometry of the spacetime you now occupy. Your path through spacetime simply has nowhere else to go. What that end would be like leads to the most physical part of the journey: spaghettification. On Earth, gravity feels uniform across your body. The pull on your head is nearly identical to the pull on your feet. Near a singularity, this is not true. The difference in gravity over a small distance becomes extreme. As you fall feet first, the gravitational pull on your feet becomes much stronger than the pull on your head. This difference is called a tidal force. Inside a black hole, these forces become immense. Your body would be stretched vertically and compressed horizontally. The process, known as spaghettification, would stretch any object into a long, thin stream of matter long before it reached the center. It would be a final, quiet disassembly at the hands of a physics we no longer recognize. This is the end of the story as told by general relativity. A complete breakdown of space, time, and matter. It is a dead end. But in science, a dead end is often a signpost, pointing toward a new and undiscovered landscape. If this quiet journey into one of the deepest questions in physics is something you find interesting, consider liking the video and subscribing to the channel. And wherever you are right now, whether in a city, a quiet room, or somewhere in between, feel free to share where you're listening from. Now, let's return to that boundary of our knowledge, and the search for a new way forward. A new kind of physics. For a long time, the singularity was accepted as a deeply strange but necessary part of Einstein's theory. But to many physicists, a true physical infinity is not a feature of the universe. It is a sign that a theory is being pushed beyond the domain where it applies. It is a signal that a piece of the story is missing. The modern search for that missing piece is focused on a new kind of physics that can unite the world of the very large with the world of the very small. The new direction is called quantum gravity. General relativity is a classical theory. It describes space-time as a smooth, continuous fabric. But the other great pillar of modern physics, quantum mechanics, tells us that at the smallest scales, reality is not smooth. It is grainy and comes in discrete packets, or quanta. The problem is that these two theories speak different languages. What happens when spacetime becomes so curved and energetic, as it does in a singularity, that its own quantum nature can no longer be ignored? This is where a theory of quantum gravity is needed. We do not have a complete theory yet, but there are promising paths, and all of them suggest the singularity is not the end of the story. They suggest the error is actually a place where a new kind of physics takes over, smoothing out the infinity predicted by Einstein. One of the leading ideas is string theory. In string theory, the fundamental parts of the universe are not points, but tiny, vibrating, one-dimensional strings. Different vibrations of these strings appear as all the different particles we see. Crucially, one of these vibrations corresponds to the graviton, the hypothetical quantum particle of gravity. In this way, string theory naturally includes a quantum description of gravity. From this perspective, one possibility is the fuzzball model. Here, a black hole is not empty space with an infinite point at the center. Instead, the entire region inside the event horizon is a tangled, chaotic ball of strings. The singularity disappears, replaced by a complex quantum object. Another leading approach is loop quantum gravity, LQG. This theory attempts to quantize spacetime itself. In LQG, the smooth fabric of spacetime is, at the most fundamental level, made of discrete, indivisible units of space, woven into a network. From this perspective, a collapsing star does not crush down to an infinite point. It crushes down until it reaches the smallest possible volume allowed by the theory. At that point, quantum gravity would create a powerful repulsive force, stopping the collapse. The singularity is avoided and replaced by what is sometimes called a Planck star. Some versions of the theory even suggest this ultra-dense object could bounce and begin expanding, perhaps forming a new universe. The singularity, in this view, is not an end, but a bridge. These ideas are still developing, but they share a common message. The singularity is likely an illusion, an artifact of using a classical theory to describe a quantum phenomenon. The case for the singularity is not as closed as we once thought. Even after a century, the deep secrets of Einstein's equations are still being uncovered. This modern investigation offers a new perspective. The singularity is no longer seen just as an endpoint, but as a clue. It is perhaps the most important clue we have, telling us where we need to dig to find a new, more complete theory of reality. But this is not the only mystery the singularity has left for us. It has a twin, a puzzle so deep it challenged the foundations of quantum science. The question of what is lost. In the early 1970s, Stephen Hawking was studying how quantum fields behave near the edge of a black hole's event horizon. What he discovered would begin a quiet, half-century-long debate at the heart of theoretical physics. He discovered that black holes are not completely black. They have a faint glow. According to quantum mechanics, empty space is a quiet sea of virtual particles that appear and disappear. Hawking realized that if a pair of these particles appeared at the edge of an event horizon, one could fall in while the other escaped. To a distant observer, it would look as though the black hole itself was emitting a particle. This slow trickle of particles is known as Hawking radiation. This radiation carries away energy, which means the black hole is constantly losing mass. Over immense, almost unimaginable timescales, a black hole would radiate away its entire mass and evaporate, disappearing in a final, quiet puff of radiation. And with this realization, Hawking had found a profound paradox. In quantum mechanics, there is a fundamental principle that information can never be truly destroyed. It can be rearranged, but it is never lost. This is a core idea called unitarity. If you throw a book into a black hole, the information it contains, every word, every atom, is now inside the event horizon. Eventually, the black hole evaporates. But what is the Hawking radiation made of? Hawking's initial work suggested the radiation is thermal and almost random. It contains no trace of the book, or of the star that formed the black hole. When the black hole is gone, the information seems to be gone with it. Forever. This is the black hole information paradox. It presented a deep conflict. Either general relativity or quantum mechanics had to be incomplete. For decades, physicists debated this problem. Hawking himself first believed the information was truly lost. He famously made a bet with physicists Kip Thorne and John Preskill, arguing that information was destroyed. But over the years, new ideas emerged, pointing toward a solution. One of the most powerful is the holographic principle. Proposed in the 1990s, it suggests that all the information inside a volume of space can be described by a theory on the boundary of that region. For a black hole, this suggests the information of whatever falls in is not lost in the 3D interior, but is somehow encoded on the 2D surface of the event horizon. In 2004, Hawking announced that he had been wrong, conceding the bet. He had come to believe that subtle quantum effects at the event horizon could allow information to escape, resolving the paradox. More recently, the story has taken another turn with the idea of entanglement islands. This concept suggests that deep inside an old black hole, a region of its interior becomes quantum mechanically linked with the radiation that has already escaped. When you calculate the information in the radiation, you must include this island. This effectively creates a path for information to get out. The calculations show that when these islands are included, information is preserved. The paradox is resolved. The information paradox, which was born from the existence of the singularity, has pushed physicists to develop new ideas about the nature of spacetime, information, and the deep connections between gravity and quantum mechanics. The limit in our understanding turned out to be a quiet guide, pointing toward a deeper level of reality. The echo of the beginning. The singularity is not just a localized question, confined to black holes. Its echo can be found at the very first moment of our universe. When we look out at the cosmos, we see that it is expanding. As observers, we can run the clock backward. If we rewind the expansion, all the matter and energy in the universe gets closer together, hotter and denser. If we follow the logic of general relativity all the way back, we arrive at the same conclusion we found inside a black hole. A point of infinite density and temperature, where all of space and time were compressed into a dimensionless point. The Big Bang singularity. The physics that falls silent at the heart of a black hole is the same physics that falls silent at the birth of our universe. The question is the same. This is a quiet but profound connection. It means that the mystery of the singularity is the key not only to understanding the fate of matter in a black hole, but also to understanding our own cosmic origin. A theory of quantum gravity that resolves the black hole singularity would, at the same time, give us a theory of the Big Bang. It would allow us to ask questions that have long belonged to philosophy. What happened before the beginning? Where did our universe come from? The singularity, therefore, is not a small, technical problem. It represents the boundary of our knowledge, the edge of our map. It is the place where our two greatest descriptions of the world, general relativity and quantum mechanics, meet and show us that they are both parts of a larger, more fundamental story. Finding that story is the ultimate goal of fundamental physics. An unfinished story. We began with a quiet place, a point where our language for the universe runs out. We journeyed through a cosmic collapse, met the minds who found the question, and explored a reality where space and time themselves change character. We have seen how this single limit in our theories has led us to other deep puzzles, and how the search for answers has led to some of the most profound ideas in science. The case of the singularity is still open. It is one of the great unfinished stories in all of science. But it is not a story of failure. The singularity is not a flaw in the universe, it is a clue. It is a message, written in the language of mathematics, telling us that our understanding of reality is incomplete. It is an invitation, pointing us toward a deeper and more unified description of the cosmos, a theory of quantum gravity. The quest to resolve the singularity is the quest to find this theory. It is a search that inspires us to build incredible instruments and to fill blackboards with equations that touch on the nature of existence itself. At the heart of every black hole, our physics falls silent. But in that silence, there is an incredible opportunity. It is the promise of a new understanding that will explain not just the centers of stars, but also the dawn of our own universe. The place where our story ends, it turns out, might just be the key to a new beginning. And the human drive to understand it, to complete that story, is a quiet and persistent force. Your information may not survive a black hole. In the quiet, vast emptiness of space, there are structures of immense gravity. They are not made of flesh or teeth, but of warped spacetime and shadow. They are black holes. For a long time, we thought we understood them. They were simple, inescapable regions in the universe. But that understanding was incomplete. The story we're about to explore is one of a deep question in physics. A question that touched two of its most important ideas. Einstein's theory of general relativity, which describes the universe on a large scale, and quantum mechanics, the laws of the very small. At the heart of this question is a simple, unsettling thought. Can something be truly erased from existence? Can the story of a thing be lost forever? Quantum physics, one of the most successful theories in science, makes a fundamental promise. It says that the information of your life, every atom that makes you you, is written into the fabric of the cosmos. It can be scrambled, it can be hidden, but it can never be truly lost. This is a core principle of how reality seems to work. But black holes, these gravitational phenomena, appear to violate that principle. They might be the universe's ultimate shredders, and for 50 years, a quiet, careful effort has been underway to discover if existence can be permanently erased. The paradox is born. To understand this problem, we first need to understand what physics means by information. This isn't about computer code or words in a book. In quantum mechanics, information is the unique and complete description of a physical system. It's the list of properties for every particle, its position, its momentum, its spin. It is the universe's own blueprint. There is a principle in quantum mechanics called unitarity. It is a technical word for a simple, profound idea. The universe does not forget. Unitarity means that if you know the exact state of a system now, you can, in principle, know its state at any point in the past or future. Every cause has a unique effect, and every effect can be traced back to a unique cause. If you burn a book, for example, it might seem that the information inside it is gone. But according to quantum mechanics, it is not. The information from the cover, the pages, the ink, is still there, just scrambled and dispersed among the smoke, the ash, and the heat. A sufficiently powerful instrument could, in theory, gather all of those products and reconstruct the original book. Information, in this view, is conserved as rigorously as energy. It cannot be created or destroyed. For most of the 20th century, this was a settled part of physics. Then, in 1974, a young Stephen Hawking began studying black holes in a new way, and uncovered a deep puzzle. Hawking wasn't trying to challenge this principle. He was simply trying to understand what happens when the rules of quantum mechanics are applied to the edge of a black hole, the event horizon. This is the point of no return. Imagine a river flowing toward a waterfall. Far upstream, you can move around freely. But as you get closer, the current gets stronger. At some point, you cross a line where the water is moving faster than you could ever swim. The event horizon is that line in spacetime. Once it is crossed, all paths lead inward, toward the singularity at the center. Classically, nothing escapes a black hole. They are perfectly black, but Hawking discovered something unexpected. He realized that the vacuum of space, which we think of as empty, is actually filled with pairs of virtual particles that constantly pop into existence before quickly annihilating each other. This happens everywhere, all the time. But near an event horizon, something different can occur. A pair of particles can be created right on the edge. One particle might fall into the black hole, while its partner escapes into space. To a distant observer, it looks as though the black hole is slowly emitting radiation. This steady trickle of particles is what we now call Hawking radiation. This was a revolutionary discovery, but it came with a difficult implication. For this to happen, the black hole must slowly lose a tiny amount of mass. Over unimaginable timescales, trillions of years and longer, this slow leak of energy will cause the black hole to shrink and eventually evaporate completely. Black holes are not eternal after all, they are mortal. And this is where the puzzle took shape. What happens to all the information that fell into the black hole? Think of all the stars and planets a black hole consumes. Each carried a unique quantum description. But Hawking's calculations showed that the radiation coming out is thermal. It is random. It contains no information about what fell in, only the black hole's mass, charge, and spin. So, imagine you throw two different encyclopedias into a black hole, one about baseball, one about botany. The black hole forms and then slowly evaporates. According to Hawking's 1974 calculations, the radiation that comes out would be identical in both cases. When the black hole is gone, the information that made the encyclopedias different is also gone. Not scrambled, but deleted from the universe. This was the problem. It suggested that information could be permanently destroyed. This struck at the foundations of quantum mechanics, the principle of unitarity. If information is lost, the past is no longer uniquely tied to the future. Cause and effect begin to break down. The ability to predict the future with certainty dissolves. The black hole information paradox was born, and it placed Einstein's theory of gravity in direct conflict with quantum mechanics. For decades, physicists would try to find a way to resolve it. The battle for reality proposed solutions. The information paradox created a deep division in physics. On one side were those who trusted Einstein's description of smooth, information-destroying black holes. On the other were those who believed the principle of quantum mechanics was non-negotiable. The debate continued for years, famously leading to a bet in 1997 between Stephen Hawking and Kip Thorne, who sided with information loss, and John Preskill, who believed information must be conserved. The prize was an encyclopedia of the winner's choice, a quiet nod to the thing they were arguing about. Solving the problem required entirely new ways of thinking about space, time, and gravity. Several ideas emerged, each one stretching the boundaries of what seemed possible. The holographic heresy. The first, and perhaps most influential, idea sounds like it comes from science fiction: the holographic principle. Proposed by Gerard T. Hooft and developed by Leonard Susskind, the idea is as elegant as it is strange. It suggests that our perception of a three-dimensional universe might be an illusion. All the information contained within a volume of space, it posits, can be described by a theory that lives on the two-dimensional boundary of that region. Think of a hologram on a credit card. It's a flat surface, but it produces a three-dimensional image. The holographic principle suggests the universe might work in a similar way. In the context of a black hole, this principle suggests that when an object falls in, its information doesn't get lost in the 3D interior. Instead, it gets encoded onto the 2D surface of the event horizon, like data saved to a disk. The information never truly crosses into a place from which it can't escape. It stays on the surface, ready to be subtly encoded into the outgoing Hawking radiation as the black hole evaporates. The information isn't lost, it's just projected. This idea gained significant support in 1997 when physicist Juan Maldacena discovered a concrete mathematical example called the ADS-CFT correspondence. It is a kind of dictionary that translates between two different theories. One is a theory of gravity in a 3D volume. The other is a quantum theory on the 2D boundary of that space. What Maldacena found was that everything that happens in the 3D world of gravity has a perfect equivalent in the 2D quantum world. A black hole forming and evaporating in the 3D space is perfectly mirrored by a system of quantum particles on the 2D boundary. And since that quantum theory conserves information, the black hole in the 3D space must conserve it too. This was a major shift in the discussion. It provided a mathematical framework for how information could escape. It was so compelling that in 2004, at a conference in Dublin, Stephen Hawking announced he had been wrong. He conceded the bet to John Preskill, presenting him with a baseball encyclopedia, admitting that information must not be lost after all. The paradox was not yet solved, but the holographic principle suggested a path toward a solution. The fuzzball revolution. While holography was gaining ground, another, even more radical idea was being developed, stemming from string theory. String theory suggests that the fundamental parts of the universe are not points, but tiny, vibrating strings. Samir Mathur and his colleagues asked a simple question: what is a black hole actually made of? The answer, they proposed, was nothing like the classical picture. Instead, they argued that a black hole is a fuzzball, a giant, tangled ball of strings that fills the entire volume of what we would call the event horizon. In the fuzzball model, there is no singularity and no sharp event horizon. There is just a fuzzy, quantum surface. When something falls into a fuzzball, its own strings merge with the tangled mass, and its information is added to the whole object. The surface of this fuzzball vibrates, and as it does, it radiates energy. This radiation is not random. Its properties are determined by the specific quantum state of the fuzzball. As the fuzzball radiates and shrinks, it does so in a way that carries the information of what it's made of back out into the universe. From this perspective, the information paradox was an illusion, created by using an oversimplified model of a black hole. If black holes are fuzzballs, information is never isolated behind a one-way barrier. It is stored on a physical surface and slowly released. Hawking's final stand: soft hair. Even after conceding his bet, Hawking continued to think about the problem. In his final years, he and his collaborators developed a third, more subtle idea, known as soft hair. A classic idea in physics is the no-hair theorem, which states that a black hole is defined by only three properties: its mass, charge, and spin. They're bald, with no other features. This is why information seemed to be lost. But the new idea proposed that black holes might have a very subtle kind of hair after all. This hair would be made of zero-energy quantum particles, like gravitons or photons, that sit at the event horizon. They found that when a particle falls into a black hole, it leaves a faint imprint on the horizon, creating a cloud of these soft particles that records the information of what fell in. This cloud would then gently modify the outgoing Hawking radiation, allowing it to carry the information away. The information isn't lost, it's stored in a ghostly aura around the horizon. These ideas all pointed in the same direction: information should survive. But for years, none of them could provide a final calculation to show exactly how it got out. The question remained open. To move forward, physicists needed a new tool, a new piece of the puzzle that could finally show the complete story of information's journey. The plot twist: the page curve and the island. For a long time, the debate was largely theoretical. The key to breaking the stalemate had been proposed back in 1993 by a physicist named Don Page, but the tools to prove it didn't exist yet. Page thought about the problem using quantum entanglement. Entanglement is a connection that links two particles. Measuring a property of one instantly influences the other, no matter how far apart they are. When Hawking radiation is produced, the escaping particle is entangled with its partner that fell into the black hole. As a black hole evaporates, the amount of entanglement between the radiation outside and the black hole's interior grows. A measure of this entanglement is called entropy. You can think of it as a measure of how much information is missing from a system. As the black hole emits more radiation, this entropy goes up, just as Hawking's calculation predicted. But Page realized that if quantum mechanics holds true, something must change. He argued that after the black hole has evaporated to about half its original size, a point now called the Page time, the entropy of the radiation should stop increasing and start to decrease. This is because newly emitted particles would start to be entangled with the radiation that was already emitted. The later radiation would carry information about the early radiation. As this happens, the overall entropy of the radiation goes down, until it reaches zero when the black hole is gone. If you plot this entropy over time, you get a rising and then falling curve. This is the famous Page curve. For nearly 30 years, reproducing this curve was a central goal. Everyone who believed information was conserved knew that a correct calculation must produce it. But no one could figure out how. Then, in 2019, a breakthrough came. In a series of papers, physicists found a new way to do the calculation. They found the island. Using a technique from quantum gravity, they found that in their calculations for the entropy of the radiation, they had to include strange new configurations called replica wormholes. These are tiny, quantum wormholes that connect the interior of the black hole directly to the Hawking radiation far away. This connection carves out a region inside the black hole, a region they named the island, that is, from an information perspective, considered part of the radiation, not the black hole. This is a subtle and deeply strange idea. The island is still physically inside the event horizon. But because of these wormhole connections, its quantum information is accessible to the radiation outside. Here is how it reproduces the Page curve. At early times, these wormholes are not important, and the entropy increases, just as Hawking predicted. But after the Page time, the replica wormholes and the island they create become the most important part of the calculation. When you recalculate the entropy of the radiation and now include the island as part of the radiation system, the result changes. The entropy stops rising and starts to fall, perfectly tracing the downward slope of the Page curve. This was a monumental step forward. For the first time, a calculation based on fundamental principles of gravity and quantum mechanics showed a way for the page curve to be produced. It didn't rely on the specifics of fuzzballs or any one model. It showed that information could be saved. Unitarity could be preserved. The encyclopedia isn't burned. It's just written in a quantum code that takes half the lifetime of a black hole to decipher. While it was a major breakthrough in theoretical models, the full picture for real black holes in our universe is still being explored. The holographic universe. So, does your information survive a black hole? The answer, according to the revolution that has swept through physics, appears to be yes. Black holes are not the universe's ultimate shredders. They are its most sophisticated scramblers. They take in information, process it in ways we are only just beginning to understand, and then slowly release it back into the cosmos. Stephen Hawking lost his bet, but his paradox set in motion a 50-year quest that has brought us to a new and deeper understanding of reality. The apparent conflict between general relativity and quantum mechanics seems to be resolving not in a victory for one side, but in a strange and beautiful synthesis. The discovery of islands and replica wormholes shows how the principles of quantum mechanics can hold, even in the face of the most extreme objects in the universe. But this solution leaves us with a legacy that is arguably even more mind-bending than the problem it solved. The holographic principle, which guided physicists toward the answer, suggests a universe far stranger than we imagined. If the information of a three-dimensional black hole can be fully described by the physics on its two-dimensional surface, what does that say about the rest of the universe? Some physicists now seriously consider the possibility that our entire three-dimensional reality is itself a kind of holographic projection. That the fundamental laws of nature are written not in the 3D space we experience, but on some distant, two-dimensional boundary. We might be the complex hologram projected from a simpler, lower-dimensional reality. This is a direction pointed to by our deepest understanding of gravity and quantum mechanics. The black hole, once a symbol of ultimate loss, has become a clue, a stone for deciphering the nature of reality. It has taught us that space and time are not as fundamental as we once thought. That the universe is woven together by threads of quantum information, connecting the inside of a black hole to radiation billions of miles away. The story of the universe, it seems, is written in a language we are all just beginning to learn how to read. What Stephen Hawking got wrong about black holes. The name Stephen Hawking brings to mind a quiet presence, a mind that traveled into the deepest parts of the cosmos and brought back ideas that gently reshaped our picture of reality. He is the author of *A Brief History of Time, a book that sits on countless shelves, a quiet testament to a shared curiosity about the universe. For decades, he was a guide, a person who looked at the universe's most profound puzzles and returned with answers. But sometimes, an answer can create an even deeper question. His most famous discovery, the one that ensured his name would be remembered, was not a final statement. It was the beginning of a new story. It was an idea so clear and so powerful that it revealed a subtle tension at the very heart of physics, a quiet disagreement between our theory of the large, general relativity, and our theory of the small, quantum mechanics. Hawking showed us that black holes, once thought to be eternal prisons, were not eternal at all. He found that they have a faint warmth, that they shrink, and that, over immense timescales, they disappear. But in discovering this, he uncovered something unexpected. He had stumbled upon a scenario where the universe's most fundamental rules seemed to be broken, where the very essence of things, what physicists call information, could be erased from existence. And that presented a very deep problem. So, what did Stephen Hawking get wrong? The answer is not a simple error. It is more like a clue, a path that leads away from our familiar picture of the cosmos and toward a stranger, quieter reality. A reality of cosmic fuzzballs, a holographic universe, and the gentle idea that spacetime itself might be woven from quantum threads. This is the story of the information paradox he revealed, and the patient, ongoing search to resolve it. A quiet discovery and the old order. To understand the question Hawking raised, we must first understand the universe he began with. For much of the 20th century, black holes were objects of finality. They are formed from the collapse of massive stars, creating a region of spacetime so dense that its gravity becomes absolute. Imagine an object so massive that to move away from it, you would need to travel faster than the speed of light. Because nothing can travel faster than light, nothing that enters can ever leave. This is the simple, stark definition of a black hole. Around it lies a boundary, a line of no return called the event horizon. It is like the edge of a waterfall in the river of spacetime. Far away, you are safe. But if you cross that edge, you are drawn toward the center, toward a point of infinite density called the singularity. In this classical view, described by Einstein's theory of general relativity, the event horizon is a one-way passage. Information can go in, but it can never come out. A star, a planet, a book. Once they cross the horizon, their unique arrangement of particles is lost to the outside world. All that remains, from an outside perspective, is the black hole's mass, its spin, and its charge. Physicists call this the no-hair theorem. Black holes are simple, bare objects, with no features to tell you what they are made of. For a long time, this was the accepted picture. Black holes were permanent and simple. They were the universe's final resting places. But in the early 1970s, a young Stephen Hawking began to think about what might happen if the strange rules of quantum mechanics were applied to this picture. This was a subtle but revolutionary step. General relativity describes the large and the smooth, planets, stars, and the graceful curve of spacetime. Quantum mechanics describes the small and the uncertain, atoms, electrons, and a world of probabilities. The two theories work perfectly in their own domains, but they do not easily speak the same language. Finding a unified theory of quantum gravity remains one of the deepest ambitions of physics. Hawking decided to ask a quiet question. What does the space at the very edge of an event horizon look like from a quantum perspective? According to quantum field theory, even empty space is not truly empty. It is filled with a constant, gentle hum of activity. Pairs of virtual particles, a particle and its antimatter counterpart, are always popping into existence, borrowing energy from the vacuum, before quickly meeting and vanishing again. This happens everywhere, all the time. It is the baseline state of reality. Hawking realized that something unique must happen if one of these pairs appeared right at the edge of an event horizon. Imagine one particle appearing just inside the horizon, while its partner appears just outside. The one inside is trapped and falls toward the singularity. But the one outside is now alone. With its partner gone, it can no longer vanish. It becomes a real particle and radiates away into space. To a distant observer, it would look as though the black hole itself was faintly glowing. This is where the insight deepens. The particle that fell in can be thought of as having negative energy. When it is absorbed, it reduces the black hole's mass by a tiny amount. The particle that escaped carries positive energy away. To keep the universe's books balanced, the black hole must pay for the escaping particle's existence by giving up a tiny fraction of its own mass. This process, repeated over and over for an almost unimaginable length of time, means that black holes are not truly black. They emit a faint thermal glow. And because they are radiating energy, they are slowly, incredibly slowly, evaporating. This is Hawking radiation. This discovery, published in 1974, sent a gentle ripple through the world of physics. It was the first real prediction to come from the careful marriage of general relativity and quantum mechanics. It meant that black holes were not eternal. Given enough time, they would radiate away all their mass until they disappeared in a final, quiet puff of energy. Stephen Hawking had changed the destiny of the universe's most permanent objects. He had given them a finite life. But in doing so, he had revealed a problem far more subtle than an eternal prison. He had found a paradox that seemed to test the foundations of science itself. The unforeseen question. Hawking's discovery was a landmark insight. But as physicists contemplated its meaning, a quiet but deeply unsettling question began to emerge. If a black hole can evaporate and disappear, what happens to the information about everything it swallowed? This is the black hole information paradox. To understand its implications, we need to be clear about what physicists mean by information. In physics, information is not just knowledge, like the words in a book. It is the complete quantum state of a system, the precise position, velocity, and spin of every particle that makes it up. It is the unique blueprint that distinguishes one thing from another. One of the most fundamental principles of quantum mechanics is that information is always preserved. It can be rearranged or scrambled, but it can never be truly erased from the universe. Think of burning a book. You might assume the information is destroyed. But in principle, if you could collect every particle of smoke, every photon of light and heat, and every atom of ash, you could reconstruct the original book. The information is not gone. It has just become incredibly difficult to read. The laws of physics, at their most basic level, are reversible. This principle, sometimes called unitarity, is the bedrock of quantum theory. If information could be lost, the world would become fundamentally unpredictable. Effects could occur without causes. The logical structure of the universe would unravel. And this is precisely the problem that Hawking's discovery seemed to present. The paradox can be stated simply. 1. According to general relativity and the no-hair theorem, all the unique information about what falls into a black hole is hidden behind the event horizon, inaccessible to the outside. 2. According to Hawking's calculation, the radiation that escapes is thermal, meaning it is completely random and contains no information about what fell in. 3. When the black hole finishes evaporating, all that is left is this random, information-free radiation. The original information about the matter that formed the black hole appears to have vanished completely. This was not a loud, dramatic explosion, but a quiet, profound contradiction between our two best theories of the universe. General relativity suggested the information was trapped inside. Quantum mechanics, through Hawking's own calculation, showed the black hole would disappear, but the information did not seem to get out. This implied that the information was simply gone. This conclusion was so unsettling that it sparked a long and thoughtful debate, what some have called the Black Hole War. On one side was Stephen Hawking, who for many years believed that information was one of the few things truly lost in a black hole, a unique exception to the quantum rules. On the other side were physicists like Gerard 't Hooft and Leonard Susskind, who felt that the laws of quantum mechanics must hold true, without exception. They argued that the information had to be preserved, even if they did not yet know how. The discussion continued for years. Then, in the late 1990s, new ideas from the frontiers of physics began to suggest a path forward. Finally, at a 2004 conference in Dublin, Stephen Hawking publicly reconsidered his position. He announced that he believed the information was not lost after all. He had been mistaken. He even settled a famous bet with physicist John Preskill, not with money, but with a baseball encyclopedia, a gift chosen because it was a volume from which information can be retrieved at will. Hawking's concession was a turning point, but it was not a final answer. It was a statement of faith that the principles of quantum mechanics would hold. The question was no longer if information escapes a black hole, but how it does so. The debate was over, but the quiet, difficult work of finding the mechanism had just begun, and it would lead physics into its most unfamiliar territory yet. So, we have a quiet puzzle on our hands. a deep question that arose from the intersection of our laws of gravity and our laws of the quantum world, all sparked by Stephen Hawking's brilliant insight. The search for an answer has asked scientists to rethink the nature of space, time, and reality itself. If this kind of calm exploration into the universe helps you unwind, consider subscribing to the channel. We look into these deep questions regularly, and the possible solutions are even stranger than the problem. The search for an answer. With Hawking's concession, the scientific community felt a sense of relief, but the true work was only starting. If information escapes a black hole, it must leave a trace. The search for this escape route has led to some of the most subtle and profound ideas in modern science. They are not small adjustments to the old picture. They are quiet rewrites of what we thought reality was. Let's explore some of the paths that have been followed in the search to resolve the information paradox. The universe as a hologram. The first important clue came from an unexpected place: the thermodynamics of black holes. In the early 1970s, before Hawking's discovery, a physicist named Jacob Bekenstein was thinking about a black hole's entropy. Entropy is a measure of hidden information, the number of ways you can arrange the internal parts of a system without changing its outward appearance. Bekenstein noticed something very strange. He found that a black hole's entropy was not proportional to its three-dimensional volume, as one might expect. Instead, it was proportional to the two-dimensional surface area of its event horizon. This was a deeply counterintuitive result. It was as if all the information about everything that had ever fallen into the black hole was not stored inside its 3D space, but was somehow recorded on its 2D surface. It is like saying the information content of a room is determined not by the space within it, but by the area of its walls. At first, many physicists, including Hawking, were skeptical. But Hawking's own later calculations confirmed it. The entropy was indeed proportional to the horizon's area. This quiet insight gave rise to a revolutionary idea, championed by Gerard T. Hooft and Leonard Susskind: the asterisk holographic principle. This principle suggests that the reality we perceive in three dimensions might be a projection of information stored on a distant, two-dimensional surface, much like a 3D hologram is generated from a 2D film. In this view, when something falls toward a black hole, its information does not truly cross the event horizon into a lost interior. Instead, it gets encoded onto the surface of the horizon itself. The 3D object is gone, but its 2D information blueprint remains. The interior of the black hole, in this sense, may not exist in the way we imagine. It could be an illusion, a projection of the information living on its boundary. This idea remained speculative until 1997, when the physicist Juan Maldacena found a powerful mathematical example of this principle. It is now known as the *ADS CFT correspondence. Though the mathematics are complex, the core idea is one of translation. Maldacena showed that a theory of gravity in a certain five-dimensional universe is mathematically identical to a quantum field theory without gravity living on that universe's four-dimensional boundary. The two theories look entirely different, yet they are perfect translations of one another. They are two languages describing the same physics. For black holes, this means the complex, gravitational interior can be fully described by the quantum interactions on its surface. The information never gets lost, because, inside, is just a holographic reflection of the boundary. The Hawking radiation that leaves the black hole is not truly random. It is subtly correlated with the information on the horizon, carrying it away, piece by piece, until the black hole has evaporated and the information is returned to the universe. Black holes as cosmic fuzzballs. The holographic principle offers an elegant framework, but it still works with the classical idea of a smooth, empty event horizon. String theory, a candidate for a complete theory of physics, suggests an even more direct idea. This is the *fuzzball* proposal. Developed by Samir Mathur and his colleagues, the fuzzball idea suggests that black holes do not have a singularity or a sharp event horizon at all. Instead, what we call a black hole is a tangled ball of fundamental strings, the vibrating strands of energy that string theory suggests make up everything. From a distance, this fuzzball would have the same mass and gravity as a classical black hole, so it would look the same to us. But if you could get close to where the event horizon should be, you would not find empty space. You would find a dense, fuzzy surface with no clear boundary. In this picture, when something falls into a black hole, it is not destroyed at a singularity. Its constituent strings simply merge with the enormous tangle of the fuzzball. The information is not lost, it becomes part of the fuzzball's complex structure. The fuzzball is like one giant, incredibly complicated molecule, and its specific state holds the memory of everything it has absorbed. This resolves the information paradox in a very direct way. Since there is no true event horizon separating the interior from the rest of the universe, the information was never trapped. The surface of the fuzzball radiates energy, like any warm object. But this radiation is not perfectly random. It is subtly shaped by the fuzzball's internal structure, and so it carries the information of its contents back out into space. The fuzzball model replaces the empty void of a classical black hole with a solid, information-holding quantum object. Wormholes and entanglement. equals EPR. Perhaps the most recent chapter in this story connects the information paradox back to another of Einstein's ideas, wormholes. This solution arises from a simple-sounding but profound conjecture. equals EPR. Let's break that down. EPR refers to Einstein, Podolsky, and Rosen, who in 1935 described the strange quantum link we now call entanglement. Two entangled particles can be connected in such a way that measuring one instantly influences the other, no matter how far apart they are. Refers to Einstein and Rosen, who in the very same year explored the idea of bridges through spacetime, what we now call wormholes. For nearly 80 years, these two ideas, quantum entanglement and geometric wormholes, were seen as completely unrelated. But in 2013, Leonard Susskind and Juan Maldacena proposed a beautiful connection. equals EPR. They suggested that a wormhole connecting 2 points in space is the geometric description of two particles being quantumly entangled. Entanglement and wormholes might be two different ways of looking at the same underlying reality. This idea has everything to do with the information paradox. The particles of Hawking radiation that escape are entangled with their partner particles that fell inside the black hole. According to equals EPR, this entanglement is a tiny wormhole. Each radiated particle is connected back to the black hole's interior through one of these microscopic bridges. This has led to remarkable calculations in recent years involving what are called asterisk islands. The math is complex, but the idea is transformative. These calculations show that late in a black hole's life, a region inside the old black hole, an island, becomes gravitationally connected to the radiation that is now far away. Through this network of tiny wormholes, the information within the island is effectively passed to the distant radiation. A pathway opens, allowing the information to escape. For the first time, these calculations showed, within the language of gravity itself, how the information could get out, confirming a long-held belief about how the process should work. The new frontier. So what did Stephen Hawking get wrong? The phrase itself feels too simple. His work was not wrong in the way of a mistake. It was an insight so profound that it revealed a seam in our understanding of the universe. His initial conclusion that information was lost was a position he later corrected with intellectual grace. But the paradox his work created was a gift. It was a signpost pointing to the exact place where our two greatest theories no longer agree, and where a new, deeper idea is needed. The information paradox is not just an abstract puzzle. It is an engine for discovery. The quiet search to resolve it has led us to consider that the universe is far stranger and more subtle than we knew. Is reality a hologram? Are black holes not holes at all, but unimaginably complex objects made of string? Is the fabric of spacetime itself held together by the quiet connections of quantum entanglement? We do not have the final answer. These different ideas may turn out to be different descriptions of the same underlying truth. But it is clear that black holes are not where information goes to die. They are laboratories for testing our deepest ideas about reality. Stephen Hawking did not give us the final word on black holes. He gave us something more important, a better question. By showing us where our theories faltered, he pushed physics toward a new and quiet frontier. The search for what happens to information at the event horizon has become a search for the code of reality itself, a journey that is slowly transforming our understanding of the cosmos.